Hello there and welcome to Physics with William, where difficult ideas are allowed to slow down a little, where the universe gets unpacked without any hurry, and where science can be both quietly fascinating and a rather good companion at the end of a long day. Tonight we are stepping into a question that sounds like it belongs in a late-night science fiction film, the kind where someone in a lab coat stares at a blinking screen and says something that makes everyone else drop their coffee. Did CERN just find a particle that exists before it is created? It is the sort of claim that sounds too dramatic to be true, and in the most literal sense it is. No one at CERN has found a particle that simply appears from nowhere, lounges about ahead of schedule, and then waits politely for physics to catch up. But there is a reason people are tempted to say things like that, and the reason is much more interesting than the headline. Because once you get close to the smallest pieces of reality, once you start looking at antimatter, quantum processes, time symmetry, and the brief wild lives of particles that exist for less than the blink of an eye, ordinary common sense begins to wobble a little. Cause and effect, which usually behave themselves so nicely in daily life, can start to look less tidy. Things can seem backwards. A result can appear to lean strangely toward its own origin. A particle can vanish almost as soon as it is born, leaving behind a trail that scientists reconstruct after the fact, like detectives arriving at the scene long after the culprit has fled. And somewhere in that process, if you squint just right, it can begin to look as though the universe is playing a trick with time. That is the mood surrounding this topic, and I think mood matters here. Because if we rush in too fast, if we start by shouting paradox and time loop, an impossible discovery, we miss what makes the story worth telling. The real wonder is not that physics has finally proven tomorrow can happen before today. It has not. The real wonder is that the laws of nature are strange enough, subtle enough, and in some cases flexible enough in how they can be described, that serious physicists can even have conversations which, from the outside, sound a little like they have misplaced the order of events. And perhaps that is part of what makes the subject so gripping at the end of the day, when the world has gone quieter and the mind has a little more room to wander. During ordinary hours we live by an almost complete faith in sequence. First this, then that. Strike the match, then the flame. Drop the spoon, then the clatter. Press send, then immediately regret the wording. It is a system most of us trust deeply, not because we sat down one morning and reasoned our way into it, but because everything around us seems to agree. Life is built on the expectation that causes come first and effects come after. It would be difficult to make tea any other way. So when a headline hints that a particle experiment may have uncovered something that looks like the reverse, it lands with unusual force. Not just because it sounds clever or controversial, but because it prods at one of the most basic assumptions in the human mind. We are creatures that tell stories in sequence. We remember what happened, then we describe what followed. We do not naturally think in loops. We do not casually imagine that an outcome might in some strange sense help define the event that produced it. We are very attached to lines. Physics from time to time is fond of showing us curves. Before we get too far into this gentle tangle, I would love to know where in the world you're listening from tonight and what time it is for you right now. It feels fitting, does it not? A conversation about time, causality, and particles that seem to behave like they have read the script in advance. And here we all are in our own local hours, arriving from different places to meet inside the same idea. Some of you may be listening late, with the lights low and the day nearly folded away. Some may be listening in the afternoon, perhaps pretending to work while giving your brain a short holiday among quarks and paradoxes. Either way, I am glad you are here. And if this sort of slow walk through physics is your kind of thing, if you enjoy science explained without being barked at, if you like your mysteries with a side of calm rather than panic, then do consider giving the video a like and maybe subscribing as well. It helps this quiet little corner find the people who want exactly this sort of company. People who enjoy hearing about the universe just before sleep, or perhaps instead of doing the washing up. I would never presume to rank those two activities, though I will say one of them tends to involve fewer damp socks. Now, to the question itself. Did CERN just find a particle that exists before it is created? The careful answer is no. The interesting answer is not quite, but I can see why someone would say it. And the long answer, which is the one we have time for tonight, leads us through several layers of modern physics that are all strange in their own respectable ways. Part of the confusion comes from how particle physics actually works in practice. When most people picture scientific discovery, they imagine direct observation. A telescope sees a planet, a microscope sees a cell, a naturalist spots a bird and writes down that it has a surprisingly judgmental expression. Particle physics is not usually like that. At CERN, and in similar laboratories around the world, scientists do not watch particles drift by with tiny name tags attached. They collide beams of particles at extraordinary energies, create showers of even more particles, and then study the debris with detectors large enough to look as though a cathedral and a computer had a child together. The particles at the centre of these stories often live for absurdly short times. Some exist so briefly that saying they are short-lived feels almost unfairly generous. They flash into being and decay before they could ever be directly handled in the ordinary sense. What scientists record are traces, signatures, imprints, patterns in the aftermath. It is less like watching a guest arrive at a party, and more like entering the room later, seeing a broken glass, a moved chair, and a suspiciously empty dessert tray, and correctly concluding that someone very specific must have been there. That method of reconstruction is one reason particle physics can sound so eerie when described loosely. If a particle is known only by what comes out after it disappears, then the story begins, in a practical sense, with the effect. The evidence appears in the detector, and from that evidence physicists infer what must have happened an instant earlier. To everyday intuition, that can already feel slightly backwards. We see the remains first and name the cause second. Nothing miraculous has occurred, of course. The event itself still unfolded in the proper physical order. But our knowledge of it arrives in reverse. We meet the footprint before we meet the foot. Another source of the drama is that some of the mathematical tools used in physics permit descriptions that do not sit comfortably with ordinary language. There are ways of talking about antimatter, for example, that make it sound as though a particle is moving backward through time. This idea has a long and famous history. It does not mean that an antiparticle is literally a tiny rebel from tomorrow, strolling into the past with criminal disregard for scheduling. It means that in certain calculations and interpretations, describing the motion that way can be useful. Physics is full of descriptions that are valid, powerful, and also capable of causing a great deal of confusion the moment they leave the page and enter a headline. This happens because mathematics is happy to be precise without being friendly. It does not care whether a phrase will sound alarming in a thumbnail. It does not pause to ask whether someone will turn a subtle point about time symmetry into a claim that the universe has misplaced cause and effect altogether. And so, again and again, real physics gives us language that is technically meaningful within a narrow framework and wildly misleading outside it. One might say the universe does not spread misinformation, but it is occasionally unhelpful with public relations. Then there is the deeper issue, and this is where things become genuinely fascinating. Modern physics contains a number of ideas that force us to question how absolute our usual notions really are. Time symmetry suggests that some fundamental laws look much the same whether time runs forward or backward in the equations. Certain quantum interpretations allow space for retrocausal language, where future measurement settings can seem oddly entangled with what we say about past events. Experiments involving the imbalance between matter and antimatter show that nature is not perfectly indifferent to direction after all. And when we examine unstable particles that flicker into existence and vanish almost immediately, the neat story we tell ourselves about clearly defined objects moving cleanly from cause to effect becomes harder to maintain. None of that adds up to proof of time travel. I should say that early, gently, and plainly. We are not heading toward the conclusion that CERN has opened a corridor to next Thursday. We're not going to discover that the Large Hadron Collider has been receiving stern notes from its own future. What we're dealing with is something both more modest and more intellectually satisfying. We're dealing with the fact that the smallest scales of nature do not always map cleanly onto the habits of thought that serve us so well in kitchens, traffic, and email etiquette. And perhaps that is what makes this question worth spending time with. It reveals a tension between the world as it feels and the world as it is described at its deepest levels. On the human scale, sequence is straightforward. On the particle scale, sequence can become inseparable from probability, observation, symmetry, and interpretation. That does not mean reality has abandoned logic. It means logic has a broader wardrobe than we expected. Imagine for a moment standing in one of CERN's vast experimental halls, beneath the Earth, surrounded by machinery built to investigate events far too small and fast for unaided senses. Around you are magnets, detectors, electronics, cooling systems, vacuum chambers, and enough cables to make a very patient electrician reconsider their life choices. Everything is designed for one purpose: to create conditions in which fleeting particles can be produced and understood. Not held, not admired, not interviewed, but inferred. The whole operation depends on reading consequences with such care that the vanished cause can be reconstructed. Already there is something philosophically rich in that. Physics at this level becomes the art of learning what must have happened by studying what it left behind. It is not unlike history in that sense, or even memory. We do not possess the past directly. We possess records, traces, scars, recollections, ruins. We build the event from the evidence. The difference, of course, is that particle physicists are rather better at statistics than most family storytellers, and their disputes usually involve fewer arguments about who really said what at Christmas dinner in 2012. Still, the resemblance is useful. Because once you see particle physics as the study of traces left by vanishing things, the emotional force of the paradox becomes easier to understand. The particle is gone before it is really known. Its aftermath is what reaches us. In that sense, our awareness does arrive after the disappearance. Discovery trails destruction. Knowledge comes after decay. We do not witness the little drama directly. We reconstruct it from the ruins. And in a universe already full of time dilation, quantum uncertainty, and symmetries that refuse to behave in fully intuitive ways, it does not take much for that reconstruction to start sounding uncannily out of order. There is also a more human reason these stories take hold. We're drawn to the possibility that time might not be as settled as it seems. Most people, even those who would never choose to spend an evening reading about particle decays, feel some private tug when they hear that the future and the past may not be entirely straightforward. Time is the medium of our lives. It is where regret sits, where hope points, where memory stores its heavy boxes. If physics says something odd about time, even in a narrow technical sense, we feel it immediately. We may not understand the equations, but we understand the ache of wondering whether the order of things is really fixed. So tonight, as we ease into this story, I want to keep two ideas side by side. The first is that the sensational claim is not literally true. CERN has not found direct proof that an effect can simply appear before its cause in the everyday sense. The second is that the claim points toward real and serious questions in physics. There are good reasons why researchers talk carefully about time symmetry, antimatter, reverse descriptions, and the subtle ways in which quantum theory complicates ordinary narratives of what happened first. There is no need to exaggerate the science in order to find it unsettling. The genuine version is already strange enough. And that brings us to the place where this story really has to begin, not with a collider, not with a famous boson, not with antimatter or a violation hidden in the behaviour of exotic particles, but with a simpler question that sits underneath all of it. What do we actually mean by cause and effect? Why are we so certain that one must come before the other? How much of that confidence comes from deep law, and how much comes from the scale at which human beings happen to live? The closer physicists look, the more that certainty begins to demand inspection, and once we start there, With the ordinary trust we place in sequence itself, the road toward these apparently backward particles becomes much easier to follow. There is something deeply comforting about ordinary time. Not exciting, perhaps, not glamorous, certainly not the sort of thing that gets turned into a dramatic headline, but comforting all the same. Most of us move through the day with a quiet confidence that the world will continue to unfold in the proper order. Morning comes before lunch. The kettle boils after you switch it on, not before. You trip over the shoe because it was left in the hallway, not because your future self needed a lesson in tidiness. It is also natural that we almost never stop to admire how much of life depends on this simple structure. Cause first, effect second. One thing leads to another. The match is struck, then the flame appears, the glass slips, then it shatters. The message is sent, then the regret arrives, often with astonishing speed, but still technically afterward. This sequence is so woven into ordinary experience that it begins to feel less like a rule and more like the texture of reality itself. We do not merely observe it, we live inside it, we trust it. We build our routines, our laws, our machines, our stories, and our expectations around it with barely a second thought. And perhaps that is one reason why any suggestion that the order might blur, even slightly, immediately feels unsettling. It is not just a challenge to physics, it feels like a challenge to daily existence. If causes and effects do not behave, then what exactly are we meant to do with calendars, appointments, cooking instructions, or common sense? The whole arrangement of practical life depends on sequence. We plan because we assume the future has not happened yet. We remember because we assume the past has already been laid down behind us. We worry, of course, because humans are very committed to inventing new uses for time, but even worry depends on sequence. We worry now about what might happen later. We do not usually worry now about what already happened tomorrow. There is something almost domestic about ordinary time. It behaves like a reliable household system. It is there in the rise and fall of light through the window, in the rhythm of meals, in the slow approach of evening, in the way a room cools after sunset. Even people who never think of themselves as interested in science are constantly depending on a set of assumptions about order. You plant first, then the garden grows. You stir the soup, then the herbs spread through it. You stay up too late, then the next day feels unreasonably pointed in its criticism. Life gives us endless reminders that sequence matters. Children learn this in the most practical way possible. They discover, quite early, that pulling something often causes it to move, that dropping something often causes an adult to sigh, and that pressing certain buttons leads to effects which are either entertaining or forbidden. That last category usually overlaps. We do not teach causality as an abstract philosophical doctrine. We teach it through experience, through repeated contact with a world that appears to answer action with consequence. A child learns that if they let go of a spoon, it falls. They may test this idea an impressive number of times, not because they distrust physics, but because they are conducting a small and very persistent research program into the behavior of reality and parental patience. By adulthood, these expectations feel almost invisible. We stop noticing how much faith we place in order because order usually rewards that faith. The bus may be late, the printer may behave with malice, and online deliveries may wander the earth like pilgrims before arriving, but even those frustrations depend on causality. There is still a before and an after. There is still a chain, even when the chain is badly managed. We expect explanations because we expect events to arise from something. We expect results to have sources. We do not take kindly to effects that refuse to identify their causes. This, in a sense, is one of the quiet foundations of reason itself. To understand something is often to ask what led to it. Why did the bread rise? Why did the bridge fail? Why did the meeting go on for so long that it began to feel like a geological era? We search for causes because the world appears to contain them. Science itself, in the broadest sense, is built on that confidence. Not necessarily the confidence that every cause is easy to find, but the deeper belief that events are not merely scattered at random without connection. There is structure, there is dependence, there is an order to be uncovered. Even our language reveals how deeply this expectation runs. We are forever linking one thing to another. Because of this, as a result of that, this led to that, then came this. Our stories, both personal and historical, rely on sequence so heavily that removing it would leave us with something almost unintelligible. Imagine trying to describe your day with no sense of before and after. The coffee was finished before it was poured. The conversation ended before it began. You arrived after leaving, but somehow before deciding to go. It stops sounding like a report and starts sounding like either a dream or a tax document. There is a reason dreams feel so strange. In fact, part of their oddness comes from their poor manners towards sequence. Dreams leap, merge, reverse, dissolve. One room becomes another. One event explains nothing. A person who was not there suddenly is, and no one seems to mind. Cause and effect loosen their ties, and the mind accepts it while asleep in a way it would never tolerate in daylight. Only later, on waking, do we realize how strange it all was. Ordinary waking life is different. It prides itself on continuity. It expects order. It demands that the world make a minimum amount of sense, and time is the quiet host of that arrangement. Not just the clock on the wall or the numbers on a phone, but lived time, ordinary time. The feeling that moments line up and carry events along in one dependable direction. It is easy to imagine time as a kind of road simply because that metaphor feels so natural. We move from one point to the next. We do not usually expect the road behind us to send objects forward. We do not expect tomorrow to reach back and tamper with breakfast. Time in everyday experience seems to provide direction as well as duration. It tells us not just how long things take, but how they must be arranged. That sense of direction is reinforced by the world around us in countless small ways. Milk sours, leaves dry out, hot tea cools. Footprints remain after the step, not before it. You can watch an ice cube melt into water, but you cannot watch a puddle gather itself into a cube on the kitchen floor and politely return to the freezer. Ordinary life is full of processes that seem to declare, again and again, that there is a proper way for time to move. The world ages, food spoils, batteries lose their nerve, haircuts grow out. Nothing in ordinary experience suggests that these processes are likely to reverse themselves while no one is looking. The comfort in all this is not merely practical, it is emotional too. A world governed by dependable sequence is easier to inhabit. Cause and effect give us a framework for responsibility, intention, and understanding. If my action produces a consequence, then my action matters. If events follow from choices, then choices mean something. We can learn, improve, apologize, repair, prevent. All of that depends on order. A universe without dependable sequence would not just be harder to predict, it would be harder to live in morally and psychologically. Responsibility itself would go a bit foggy around the edges. This may be why people cling so strongly to ordinary time, even when physics asks awkward questions about it. On the scales that matter to human life, ordinary time works beautifully. It guides cooking, gardening, medicine, engineering, conversation, and sleep. It governs traffic lights and train timetables, and the very fragile confidence with which we tell ourselves there is still plenty of time to leave the house. It allows us to navigate the world well enough that most days we are not forced to confront the deeper strangeness hidden underneath. Because hidden underneath, as modern physics rather insists, is a more complicated picture. But before we go there, it is worth lingering a little longer with the ordinary one because it is not foolish or naive. It is earned. Human beings did not invent the comfort of ordinary causality out of laziness. We trust it because it works. If you have ever baked bread, repaired a lamp, learned an instrument, or tried to grow tomatoes, then you have lived inside a web of repeated causes and observed effects. Daily life is a long practical education in sequence. It is also a lesson in delayed consequence, which may be why adults so often seem tired. Not every effect arrives immediately. Some causes are slow and patient. A habit forms gradually. A neglected task compounds. A kind word lingers. Poor sleep accumulates like a debt collector with excellent records. Part of ordinary wisdom lies in understanding that time does not merely separate events, it also stretches them. Causes can ripple forward through minutes, days, or years. Yet even then, we still preserve the order. The cause may be distant, but it remains behind the effect, not ahead of it. This is where ordinary time becomes something more than convenience. It becomes a framework for meaning. We tell ourselves who we are by linking events across time. I did this, then I learned that. This happened, so I changed. We narrate our lives causally. It would be very hard to have an identity without sequence. Memory alone would not be enough. Memory needs arrangement. It needs a sense that one thing led to another. Even regret depends on ordinary causality. We regret because we believe something might have gone differently had an earlier cause been changed. Hope works the same way in the opposite direction. We act now because we believe later can still be shaped. In that sense, causality is not just a scientific principle, it is a psychological shelter. It makes the world feel inhabited rather than chaotic. It lets us think that understanding is possible. When something goes wrong, we ask why. That question carries a hidden promise that there is an answer, or at least that there ought to be. We would not ask it so naturally if we did not expect causes to exist. Even when we say something happened for no reason, we usually mean that we do not know the reason, or that the reason was absurd, not that the universe literally produced a result in total isolation from prior conditions. For centuries, this confidence blended very naturally with the way science described the world. The universe looked, in broad terms, like a grand machine. Objects moved, forces acted, results followed. If you knew enough, then in principle you could predict what came next. That vision of nature was powerful not only because it helped explain motion and mechanics, but because it agreed with the grain of everyday experience. It extended common sense rather than overturning it. The same world in which a rolling ball knocks over a cup is also the world in which planets move in lawful paths. The scales are different, but the order feels familiar, and even now, despite everything that has happened in modern physics, this remains true in many ordinary situations. You do not need quantum interpretations to cross a road safely. You do not need a theory of antimatter to roast vegetables. You do not need to think about time symmetry to know that forgetting to charge your phone will have consequences tomorrow that feel unfairly personal. For almost all human purposes, ordinary time remains the right tool. It is a remarkably good description of the world we actually inhabit with our bodies, habits, and plans. So when physics begins to complicate that picture, it is important not to mistake complication for dismissal. The point is not that everyday causality is an illusion in the cheap sense, as though kettles have been lying to us all along. The point is that reality may contain layers, and what is solid and dependable at one scale may become subtler at another. Water feels smooth from a distance and molecular up close. A table seems still, though its atoms are not. Ordinary time may be something like that. Stable, useful, and profoundly real in experience, even if the deeper account of it turns out to be less straightforward than the version we use while making dinner. There is also a difference between how the world behaves and how we know it behaves. In daily life, these two are usually so tightly paired that we forget they can come apart. I push the door and it opens. I hear thunder after lightning. I touch the mug and discover, too late, that the tea is still far too hot. But as science moves into stranger territory, knowledge often arrives indirectly. We no longer witness causes and effects in a simple linear sequence through the senses. We detect, infer, reconstruct. And that alone can make the order of things feel less immediate, less obvious, more open to puzzling language. Suppose, for example, that what you know first is the aftermath. A detector lights up, a trace appears, a burst of energy is recorded. Only afterward do scientists work backward to infer what unstable particle must have briefly existed to produce that pattern. Nothing physically backward has happened, but the structure of knowledge has changed. We encounter the evidence before we name the event. We see the consequence and reconstruct the cause. On the human level, that can already feel a touch uncanny, because our minds are so used to direct sequence. And then, layered over that, come the genuinely strange features of modern physics. The possibility that some laws do not care much about the direction of time. The curious way antimatter can be described in certain contexts. The tiny but important asymmetries that distinguish matter from antimatter and give the universe its lopsided preference for one over the other. The fleeting particles that exist so briefly that they are less observed than inferred. Each of these chips away, not at the practical usefulness of ordinary causality, but at its status as the complete and final story. That is why the idea of a particle seeming to exist before it is created has such force. It sounds like a direct attack on the old comfort. But more often what is really happening is subtler. Physics is not saying that your breakfast can be caused by your lunch. It is saying that, at very small scales and in very special cases, the way events are described, connected and interpreted can stretch our ordinary language further than it likes to go. And ordinary language, to be fair, likes a quiet life. Still, before we follow physics into those more difficult rooms, it helps to appreciate what it is leaving behind, or at least moving beyond. It is leaving behind the warm furniture of everyday certainty. The reassuring world where sequence behaves, time keeps order, and causes know their place. It is leaving the scale at which intuition was trained. No wonder the transition feels strange. We are like people who learned the sea from the shoreline and are now being told about currents far offshore that do not resemble the gentle waves we know. So the next step is to move from that shoreline into the place where ordinary time begins to feel less sufficient, into the giant machines and buried detectors where physicists deliberately create conditions unlike anything the human nervous system evolved to understand. There, under the ground and inside those controlled collisions, the tidy comfort of daily sequence starts to meet a world that is faster, stranger, and much less interested in reassuring us. To understand why people can come away from CERN with the uneasy feeling that common sense has been asked to wait outside, it helps to picture what is actually happening there. Not the simplified version, where a scientist presses a button and a mysterious particle politely appears for inspection, but the real place, the real machinery, the real scale of the enterprise. Because CERN is not a room with a shiny gadget in the middle. It is a vast underground effort to study events so brief and so small that the ordinary human way of learning about the world becomes almost useless. Most of what feels natural to us comes from the fact that we evolved in a very narrow zone of reality. We're good at judging the weight of a cup, the sound of footsteps, the time it takes toast to go from pale optimism to unfortunate regret. We are not naturally equipped to understand what happens when protons are accelerated to extraordinary speeds, sent in opposite directions around a machine buried beneath the ground, and smashed together in conditions that briefly resemble the deep past of the universe. That was not a challenge faced by our ancestors with enough regularity for evolution to prepare us, and yet that is what CERN is built to do. The Large Hadron Collider is a machine of astonishing scale and precision, a ring stretching for many kilometers beneath the border of Switzerland and France, cold enough in places to make outer space seem positively sociable. Inside it, beams of particles are guided and focused by powerful magnets, kept within vacuum tubes, and accelerated until they carry enormous energy. Then, at carefully chosen points, those beams cross. Protons collide. New particles can emerge. Others decay almost instantly. And in the middle of all this violence, physicists try to learn what happened. It sounds straightforward when said quickly. It is anything but. The collisions themselves are not little fireworks visible to the eye. Nobody stands there watching a neat spark and saying, "Ah yes, there goes a Higgs boson, looking brisk this afternoon." What happens instead is that the collision produces a shower of secondary particles moving outward in different directions. These pass through giant detectors built like layered traps for information. Each layer is designed to record something different. Some track the paths of charged particles, some measure energy, some are especially good at identifying particles that can travel farther than others. The whole system functions less like a camera in the ordinary sense, and more like an enormous forensic instrument. That word matters here. Forensic. Because by the time the event is known, the original moment is already gone. The particles most interesting to physicists are often the least cooperative guests in existence. They arrive, if arrive is even the right word, and then decay almost immediately into other particles. Those daughter particles may then decay again. What the detector records is not the short-lived object in some leisurely direct fashion, but the chain of consequences it leaves behind. Physicists then work backward from those consequences to reconstruct the event. This is where common sense begins to feel a little strained. In ordinary life, we usually think we encounter causes first and then effects. I see the glass tip, then I hear it hit the floor. At CERN, knowledge tends to arrive in the opposite order. The evidence is what appears first to the scientists. A track here, a burst of energy there, a pattern of momentum that should not exist unless something very particular happened a tiny instant earlier. The cause is inferred from the aftermath. This does not mean the universe ran backward. It means the act of understanding begins with ruins. Imagine arriving at a crime scene where the suspect evaporated a fraction of a second after the deed. There is no interview, no direct sighting, no chance to ask where they were at the time of the interaction, since the answer is very likely everywhere and nowhere useful. What you have instead are footprints, fragments, timing information, and a few stubborn clues. That is modern particle physics. It is the science of learning from traces, and once you accept that, you begin to understand why its language can sound so strange. When the thing you care most about vanishes before you can point at it, the entire discipline becomes an exercise in reconstructing invisible causes from visible effects. There is something almost theatrical about the setting too. The detectors at CERN are immense, and not merely in a technical sense. They have presence. They look like machines designed by people who were told to build a cathedral for evidence. Layer upon layer of hardware, electronics, sensors, shielding, support structures, and software systems all cooperate to catch the brief signatures of particles that do not care whether we understand them. The scale is necessary because the events are so small. That contrast is one of the most striking things about CERN. To learn about the tiniest ingredients of matter, humanity has had to build some of the largest and most intricate instruments it has ever created. And even then, the process is not simply one of waiting for truth to present itself. Most collisions are not especially interesting. They produce outcomes that are already well understood or irrelevant to the specific question being asked. A small fraction contain patterns worth closer study. Smaller still are the events that might hint at something rare, subtle, or new. So the detectors do not merely record everything in some neat and permanent way. There are systems that make extremely rapid decisions about what to keep and what to discard. In a sense, the machine itself begins interpreting before any human mind has entered the scene. That too can feel like common sense has been slightly rewritten. We like to imagine observation as a calm, human act. You look, then you know. At CERN, observation is distributed across electronics, software, data filters, and later statistical analysis. The event happens, signals race through the detector, algorithms help decide whether the event is worth saving, data are stored. Analysts then sift through vast numbers of recorded events, searching for patterns that rise above the background. The final act of discovery may come much later, after millions upon millions of collisions have been examined. So there is a peculiar layering of time involved. The physical event is over almost at once, but the scientific meaning of it emerges slowly. This is part of why the place can seem to produce effects that arrive before causes, at least in spirit. not literally, not physically in the dramatic headline sense, but in the structure of human understanding. The particle, if it existed, may have lived and died long before anyone says with confidence that it was there. A Higgs boson, for example, does not linger. It decays almost immediately into other particles, and those decay products are what the detector sees. When scientists announced the discovery of the Higgs boson, they were not announcing that they had stared directly at a tidy little Higgs floating about in an obliging mood. They were announcing that a certain pattern in the debris made the existence of such a particle overwhelmingly likely. That distinction is easy to lose in casual discussion, but it matters enormously. Particle physics is not usually about direct possession. It is about inference under carefully controlled conditions. It is about asking what short-lived object best explains the data. The collision is like a sentence uttered too quickly for the ear, and the detector is left to identify the speaker by the echo, the accent, and the overturned furniture. There is also the question of scale in time. Human beings are quite attached to processes that unfold slowly enough to be narrated comfortably. The soup simmers, the day darkens, the train approaches with the sincerity that may or may not be justified. At CERN, many of the processes of interest occur on timescales so short that ordinary language begins to sound clumsy. A particle may be produced and decay again before any picture resembling a stable object could form in the imagination. This is one reason the public can be drawn toward more dramatic interpretations. If something exists for only the briefest instant and is known only through what follows, then it is tempting to describe it as ghostly, paradoxical, or somehow out of order. But the deeper truth is less supernatural and more demanding. These are not violations of logic. They are reminders that logic at this scale is mediated by probability, conservation laws, detector response, and statistical confidence. The universe is not abandoning cause and effect. It is simply refusing to stage them in a format our instincts find easy. What feels uncanny is often just unfamiliar precision. The collisions themselves also matter because of what they recreate. When protons smash together at very high energies, they can briefly produce conditions not seen in ordinary earthly life. Energy can be converted into mass. New particles can appear, provided the rules allow it. Some of these particles are familiar members of the subatomic family. Others are rarer or more unstable. In effect, CERN creates tiny bursts of extreme possibility, then watches what shakes loose. It is not recreating the early universe in full, of course, but it is probing a regime in which some of the same deep physics becomes accessible. That is a grand thing to say, but it is worth grounding in the practical reality. The actual work is not one long gasp of revelation. It is meticulous. Teams calibrate detectors, engineers monitor systems, analysts compare simulations with real data. Physicists argue about whether a pattern is significant or merely suggestive. Statistical thresholds are applied. Background processes are understood in painful detail. If a headline says CERN found something shocking, the truth behind it usually includes an astonishing amount of patience, paperwork, and people staring at plots with the concentrated expression of those who know that one careless assumption can waste months. That patience is necessary because rare events can hide inside very common ones. Imagine trying to identify a single whispered phrase in the middle of a football crowd, while also accounting for echoes, weather, microphone noise, and the possibility that half the crowd is singing. That is a bit like looking for new physics in collider data. The signal you want may be subtle. The background is enormous. Most of the work lies in proving that what seems interesting really is interesting, and not just an especially theatrical fluctuation. This is why CERN can briefly make common sense look incomplete, without actually discarding it. The place is not a factory for impossible things. It is a machine for showing that the deeper levels of reality are far less tailored to human intuition than daily life might suggest. We are used to stable objects, smooth timescales, direct observation, and simple sequences. CERN deals in unstable entities, tiny fractions of time, indirect evidence, and chains of decay that must be reconstructed from layered traces. Of course, the result feels strange. We have walked into a level of reality where the furniture is arranged for mathematics, not comfort. Antimatter offers a particularly vivid example of this. In the detector, a particle and its antiparticle may be created, travel a short distance, and then annihilate or decay into something else. These processes are entirely lawful, but the language surrounding them can sound almost fantastical. Certain ways of formulating the mathematics make an antiparticle resemble an ordinary particle, moving backward through time. Again, this does not mean CERN is catching little time travelers in the act. It means there are symmetries and descriptions in the theory that challenge the one-way story our everyday imagination prefers. Inside the detector, those abstract possibilities are not just philosophical musings. They help organize what the data mean. And data at CERN come in torrents. The volume is immense. No human could sit and absorb it event by event like an old-fashioned observer with a notebook. The science depends on automation, filtering, distributed computing, and collaboration on a truly international scale. Thousands of people contribute to the design, operation, analysis, and interpretation of the experiments. Discovery in such a setting is not a single dramatic moment in a lonely lab. It is a long social and technical process in which the universe reveals itself through collective effort. That too changes the feel of common sense. We often imagine truth arriving as a direct encounter between a person and a fact. At CERN, truth can emerge from layers of mediation. Hardware records signals, software reconstructs tracks, models predict patterns, teams compare results, statistical methods determine significance, papers are reviewed. Only then does a claim solidify. By the time the public hears about a finding, the event itself may be old in every meaningful sense except scientific importance. The world has moved on, the particles are gone, the meaning has just arrived. So when someone says that CERN found a particle that seems to exist before it is created, they are reaching, clumsily but understandably, for this whole atmosphere of reversal. The object of interest is often gone before it can be named. The evidence comes first to us, the explanation comes later. The mathematics sometimes admits descriptions that point against the everyday arrow of time. The detector records effects from which causes are reconstructed. Common sense is not broken, but it is definitely being asked to sit in a less comfortable chair. There is another subtle point here, and it helps explain why CERN is such fertile ground for paradox-flavoured storytelling. At human scales, objects feel like enduring things. A chair remains a chair long enough to be sat upon, ignored, tripped over, and blamed. At collider scales, many particles are not enduring things in that familiar sense. They are brief excitations, temporary arrangements, unstable possibilities that immediately transform into something else. Trying to apply ordinary object-based intuition to them can be misleading from the start. They are less like tiny billiard balls and more like brief events, with identities defined by how they interact and decay. Once you think that way, the whole place begins to look different. CERN is not merely smashing particles together, it is producing and deciphering momentary patterns of becoming. Some of those patterns confirm long-standing theories, some test them, some reveal tiny asymmetries that matter enormously, and some seem, at least at first glance, to toy with our deepest assumptions about time and sequence. Not because the collider is performing magic tricks underground, but because the world at that level is stitched together by rules that do not always wear their meaning on the surface. And that takes us very naturally toward the next layer of the story, because once the detector shows us a world where the cause is often known only through its aftermath, and where some descriptions already start to lean against the ordinary flow of time, it becomes possible to ask a more delicate question. What happens when quantum theory itself begins to flirt with the idea that what comes later might help define what came before? That is where the paradox sharpens, and where the language of effects arriving too soon begins to sound less like tabloid exaggeration, and more like a real problem in how we describe the smallest events at all. One of the most reliable ways to make a perfectly sensible piece of quantum physics sound like a threat to common sense is to describe it in plain everyday language without warning. Say something like, the future measurement seems to decide what the particle did earlier, and watch the room go quiet. Someone will blink. Someone else will laugh nervously. A third person, usually the one who already mistrusts modern science on aesthetic grounds, will fold their arms as if this confirms a private suspicion that physicists are mainly paid to make sentences worse. And yet the unsettling thing is that phrases like that do not come from nowhere. They arise because quantum theory really does contain situations where the order of explanation starts to feel slippery. Not broken, not lawless, not magically reversed in the cinematic sense, but slippery. The kind of slippery where you can still walk if you are careful, though you may no longer stride with the confidence you had in the kitchen a few minutes ago. This is the quantum trick at the heart of so many time paradox headlines. Under certain conditions, what happens later can seem to reach back and alter what we are entitled to say about what happened earlier. Not necessarily what physically happened in some absolute storybook sense, but what description makes sense, what path can be assigned, what causal language still feels safe, and that distinction matters more than it first appears. In ordinary life, explanation usually feels simple. You flick the switch and the light comes on. You hear the sound because the door slammed. You arrive late because you trusted a timetable that should, in fairness, be considered more of a suggestion. Everyday causality has a clear posture. It points forward. It is comfortable with sequence. It likes events to cue properly. Quantum theory, by contrast, often behaves as though the cue exists, but nobody agrees where it starts or what counts as standing in line. Part of the trouble begins with measurement. In classical life, measurement feels passive. You look at the apple and learn where it is. You weigh the parcel and discover how heavy it is. You check the time and confirm that yes, somehow the entire afternoon has vanished into errands and one unnecessary email. The act of measuring does not seem to alter the thing in any profound way. It reveals, it does not negotiate. In quantum physics, measurement is not so innocent. What can be said about a system depends in a deep way on how it is measured, what kind of question is asked, and what setup is used to ask it. This does not mean that particles sit around waiting for humans to notice them like theatrical performers with poor boundaries. It means that the properties we are tempted to imagine as fixed and settled in advance do not always behave that way. Quantum systems are described in terms of possibilities, amplitudes, and relations that only become pinned down in certain respects when an interaction corresponding to a measurement takes place. That is already strange enough. But then come the experiments that make the strangeness sound almost backward in time. Take the simple and famous case of a particle that can travel through more than one possible route in an experimental setup. If the setup is arranged in one way, the particle behaves as though both routes matter together, producing an interference pattern that tells us the alternatives were not simply exclusive in the ordinary sense. If the setup is arranged another way, the particle behaves as though one route or the other can be meaningfully distinguished. In one case, the world seems to insist on a wave-like combination of possibilities. In the other, it seems to offer a more particle-like choice. So far, odd but manageable. Now add the twist. Suppose the decision about what kind of measurement to make is delayed until after the particle has already passed the point where, according to ordinary thinking, it would have had to commit to one route or the other. Suddenly the story becomes deeply uncomfortable. If the later choice determines whether the earlier history can be described as one path or two interfering possibilities, has the future reached back and changed the past? That is the dramatic version, and it is the one that feeds the headline machine very nicely. But the careful answer is more subtle. Quantum theory may be telling us that the earlier event was never correctly described in those ordinary terms to begin with. The apparent retroactive influence comes from our attempt to force a classical narrative onto something that does not owe us one. This is where the word retrocausality begins to appear. It is a serious word, but also a dangerous one in public conversation, because it sounds far more settled than it is. Retrocausality is the idea that future events, or future measurement choices, may in some sense help determine or constrain earlier physical states. Some interpretations of quantum mechanics allow room for this kind of thinking. Others do not need it. Still others avoid the whole issue by saying our ordinary categories of cause and effect are simply not the right ones to apply so directly at that level. The important thing is that the idea exists at all within serious discussion, not as proof that time runs backward, but as a sign that quantum theory makes our usual causal language less secure than we might like. It helps to linger over why this feels so much stranger than other scientific surprises. If a scientist tells you that stars are made of hot plasma, or that space can bend, you may be impressed, but the world of causes and effect still feels roughly intact. If a scientist tells you that a later measurement choice seems to alter what can be said about an earlier event, then something more intimate is disturbed. You're not just being told a fact about nature, you are being asked to loosen your grip on sequence itself. That is harder. It reaches closer to the bones of thought, and yet the actual experiments do not require mysticism. They require discipline. Delayed choice experiments, for example, are carefully structured tests in which the experimental arrangement is altered after a quantum system has already entered part of the apparatus. The puzzle is that the later setup appears to determine whether it makes sense to describe the earlier behaviour in one classical way or another. To a mind raised on ordinary causality, this looks like the effect has arrived before the cause. But many physicists would say that nothing has arrived early. Rather, the entire experimental arrangement taken as one whole determines what kind of phenomenon the event is. The mistake is imagining the particle carried a little classical diary that was fully written before the final measurement context was set. That is a useful point because it shows how the paradox often enters through storytelling rather than data. We want a neat tale. The particle went here, then this happened, then later we checked. Quantum theory keeps objecting that perhaps the particle did not go anywhere in the classical sense that story assumes, at least not in a way you are entitled to describe before the full measurement context is considered. This is not the universe reversing time for mischief. It is the universe declining to fit inside the grammar of billiard balls and footprints. Then there is the quantum eraser, one of those phrases that sounds as though it was invented by a writer who had been told to make physics sound expensive. The central idea is that information about which path a quantum system could have taken can affect whether interference is observed. If that which path information is available in principle, the interference disappears. If it is erased, even in a carefully structured sense after the relevant event, the interference can reappear in the properly sorted data. Described badly, this sounds like the present reaches back and changes the past, as though the particle had been waiting for instructions from the future before deciding how to behave. Described carefully, it says something more precise and less theatrical. The way outcomes are grouped and interpreted depends on the total information structure of the experiment, but again, even the careful version is unsettling, because it suggests that what we call the past event is not fully separable from the later conditions under which information about it is made meaningful. The particle does not become a tiny time traveller. No message is sent backward to help someone win the lottery or avoid an unfortunate haircut. Causality in the practical sense remains safe, but the conceptual boundary between earlier and later becomes harder to describe in the plain one-direction language that served us so well in ordinary life. This is why you will sometimes hear physicists say that quantum events do not always admit a simple, underlying narrative independent of measurement. It is not that they are hiding the real story behind jargon. It is that the real story may not be the kind of story our intuition expects. We want hidden little trajectories, private facts settled in advance, a universe that politely keeps its records in order. Quantum theory keeps offering something else: relations, possibilities, correlations, constraints that span the setup as a whole. And once you start thinking in those terms, the temptation to talk about later events influencing earlier ones becomes understandable, even if one ultimately decides that such language obscures more than it clarifies. There is another layer to the discomfort, and it involves probability. In ordinary life, probability usually measures ignorance. If I say there is a chance of rain, I mean I do not know whether it will happen, though the clouds are making a fair effort to look persuasive. The rain itself either comes or it does not. In quantum theory, probability is not always so easily treated as mere lack of knowledge about a hidden classical fact. The structure of the theory treats alternatives in a way that allows them to combine, interfere, and depend on measurement context. So when a later choice alters what pattern appears, it does not necessarily reveal that a pre-existing fact has been changed. It may reveal that the earlier event was never a settled classical fact in the way we assumed. That is a difficult sentence, but it points toward the heart of the matter. The apparent reversal of cause and effect often comes from our insistence on assigning definite histories too early. We want to say the particle already did this, before we ask that question in that way. Quantum theory keeps warning that perhaps the asking is part of what makes that sentence meaningful. Not because consciousness summons reality into being with magical authority, but because interactions and measurement setups help define what properties can be sensibly attributed. There are interpretations that push this further in different directions. Some accept a kind of retrocausal picture more readily. They say that quantum correlations become less puzzling if influences are allowed to run both ways in time, or if boundary conditions from the future as well as the past help shape physical events. Others avoid that language and instead adopt a block-like view in which the whole experiment is one consistent structure, with no literal flowing influence backward, only a global consistency that our sequential minds struggle to picture. Others split the problem across branching outcomes, or deny that the wave description is the whole story, or reframe the mathematics in still other ways. The lack of a single, universally accepted narrative is not a sign of failure so much as a sign that the theory works extraordinarily well while still resisting one simple picture of what it means. And that resistance is exactly what gives the paradox its power. If you want to write a dramatic line about a particle that seems to exist before it is created, you do not need actual time travel. You need only a situation in which the later measurement context appears inseparable from the earlier description. To most people, that already sounds like the effect is arriving too soon. The quantum trick is not that causality has been obviously overturned. It is that our ordinary categories for assigning causal order no longer fit neatly over the structure of the experiment. An analogy may help, though every analogy in quantum physics eventually starts complaining about working conditions. Imagine reading a mystery novel in which the meaning of an early scene changes depending on what final chapter you read, not because the pages altered themselves, but because the later context reveals that the earlier event was never properly understood in isolation. In a weak sense, we're used to this. Endings recast beginnings all the time in fiction. But quantum theory seems to make that sort of recasting part of the physics itself, not merely a matter of human interpretation. The full setup determines what kind of event the earlier part was. That is not the same as saying the ending caused the beginning, but it is close enough in feeling to make people reach for precisely that language. This matters for our broader story, because the world of high-energy particle physics often lives downstream from these conceptual tensions. At CERN, particles are created, decay, interact, and are reconstructed through elaborate patterns of evidence. The detector records outcomes. Physicists infer histories. The mathematics used to describe these processes is shaped by the strange grammar of quantum theory. So when a claim arises that an effect seems to show up before its cause, it is not usually because someone watched a proton collision and saw tomorrow arrive early. It is because the deeper framework already allows situations where later conditions seem entangled with how earlier events can be described at all. One must also be careful not to smuggle human time perception into places where it does not belong. At our scale, waiting matters. Sequence feels lived. We have boredom, anticipation, regret, and alarm clocks. A quantum event does not possess those moods. It is not sitting there wondering whether the future has made up its mind. The language of before and after, while essential to our descriptions, may not map cleanly onto what the process is in itself. This is one reason the most careful physicists often speak in terms of correlations, amplitudes, symmetries, and measurement outcomes rather than little stories about particles choosing paths. The stories are useful, but they can become traps if taken too literally. Still, it would be too easy to dismiss the whole issue by saying that quantum theory is merely weird and should be left alone. The reason these experiments matter is that they do sharpen genuine questions about temporal order. They make it harder to say, with complete confidence, that the classical arrow of explanation is fundamental in every context. They suggest that at the quantum level, some aspects of what we call the past may only become sharply characterizable in relation to later measurement arrangements. Whether that is best called retrocausality, contextuality, or simply the failure of classical pictures is still debated. The debate itself is part of the story, and perhaps this is the gentlest way to put it. Quantum physics does not clearly tell us that effects happen before causes. What it does tell us is that the comfortable boundary between the two may not be as primitive, as simple, or as one-sided as human intuition would prefer. The quantum trick is not a theatrical reversal of time. It is a quiet refusal to let us assign ordinary causal language too early or too confidently. The later question helps define what sort of earlier answer can exist. That is already enough to make the old certainties tremble a little. Once that trembling begins, the next step almost suggests itself. If quantum theory can already make later conditions seem strangely relevant to earlier descriptions, then what happens when we turn to antimatter, where the mathematics has long tempted physicists to speak as if certain particles are moving backward through time? That idea has a reputation far larger than its literal meaning, but it sits right at the crossroads of our story, where the language of time, symmetry, and creation starts to sound more paradoxical than ever. At this point, it becomes easier to see why antimatter has acquired such a dramatic reputation. If quantum experiments already make it harder to tell a simple one-direction story about what happened first, then antimatter arrives like an especially confident guest and makes the whole conversation even stranger. It is one thing to say that later measurements can seem oddly tied to earlier descriptions. It is another to hear that, in certain mathematical ways of speaking, an antiparticle can be treated as if it were an ordinary particle moving backward through time. That is the sort of statement that immediately lights up the imagination. It sounds like a loophole in reality. It sounds like the universe has slipped and revealed a hidden seam. It also sounds, if we're being honest, exactly like the sort of sentence that demands a deep breath and several careful qualifications before anyone is allowed near a headline. Because here again, the literal dramatic version is not the right one. No physicist is watching antimatter zip cheerfully into yesterday, undoing errands and improving stock portfolios. Antimatter is real. It is measurable. It is produced in experiments. It annihilates with ordinary matter in very specific and well-understood ways. But the phrase about moving backward through time belongs to a particular mathematical interpretation, one that is elegant, provocative, and easily misunderstood. If we are patient with it, though, it opens onto one of the most beautiful and unsettling ideas in modern physics, namely that the difference between particles and antiparticles may be tied to deep symmetries in time itself. To appreciate why this idea appeared at all, it helps to remember that antimatter was not originally discovered because someone went looking for something called antimatter in the modern popular sense. It emerged from theory before it became experimental fact. That already gives it a slightly uncanny status. In the early 20th century, when physicists were trying to reconcile quantum mechanics with special relativity, the equations describing electrons produced something unexpected. They allowed solutions that looked very much like the known electron, but with opposite electric charge. At first, this was a puzzle, then it became a prediction. Eventually, the positron was discovered, a particle with the same mass as the electron but positive charge. Antimatter had arrived, not as a fantasy or philosophical game, but as a real feature of nature. That in itself was remarkable enough. The world had turned out to contain mirror versions of familiar particles. Not every detail mirrored in the simplistic sense, of course, but enough to reveal a profound symmetry. For many kinds of matter particle, there exists an antiparticle counterpart: electron and positron, proton and antiproton, neutron and antineutron, though with neutrality and internal structure making the story a bit more subtle in certain respects. These pairs can be created together under the right conditions. They can also annihilate one another, converting their mass into other forms, often bursts of high-energy radiation. Matter and antimatter meet, and both disappear into energy and new products. It is the sort of process that sounds almost mythic until you realize it is part of standard physics. Even without any mention of time reversal, antimatter already pushes common sense a little. We are used to thinking of matter as the basic stuff of the world: tables, trees, lungs, stars, coffee mugs, the regrettable contents of an overfilled drawer, all made of matter. Antimatter sounds like the shadow version of that, something more conceptual than real, perhaps a theatrical opposite invented to make equations look balanced. But it is real enough to be made in accelerators, trapped briefly in experiments, and used in certain medical technologies. The difficulty is not in its existence. The difficulty lies in how deeply strange its role appears once the mathematics is taken seriously. One of the most famous ways to think about antiparticles emerged from the work of physicists trying to understand the full implications of relativistic quantum theory. The mathematics allowed a striking reinterpretation. Under certain conditions, a particle travelling backward in time could be described equivalently as an antiparticle travelling forward in time. That sentence is both famous and dangerous. Famous because it captures something elegant and deep. Dangerous because most people hear it and immediately picture a little object literally retracing history in reverse, which is not how antimatter behaves in any ordinary observational sense. The safer way to say it is this: the equations describing particles in relativistic quantum theory admit a symmetry that makes these two descriptions mathematically related. One can represent an antiparticle as the time-reversed counterpart of a particle. In diagrams used by physicists, this can even be drawn in a way that visually suggests the antiparticle is a particle line going backward in time. Those diagrams are extremely useful. They help calculate probabilities for interactions. They organize processes in a compact and powerful way. But they are not tiny photographs of what reality looks like from the inside. They are tools. Very good tools, but tools all the same. This distinction matters because the moment the diagram becomes a literal mental picture, confusion multiplies. A line that points one way or another in such a diagram encodes aspects of the mathematical structure of the interaction. It does not mean a laboratory detector would watch a positron arrive before it was produced. In the actual experiment, what you observe is fully consistent with ordinary chronological order. A collision occurs. A particle and antiparticle may be produced. They travel through the detector. They leave signals. They may later annihilate or decay. No stopwatch trembles. No technician drops a clipboard because tomorrow appears to be leaking. The backward-in-time language belongs to the formalism. Even so, it is not empty language. It is not merely metaphor. The reason it has persisted for so long is that it reveals something deep about the symmetry of the laws involved. At the level of equations, time reversal is not always nonsense. Some processes can be described in ways that remain meaningful when the direction of time is reversed. Antiparticles sit naturally within that broader structure. Their existence reflects the fact that the underlying physics is more symmetric, more flexible in description than the one-way common-sense story we tell ourselves during breakfast. And breakfast, to be fair, remains a poor training ground for antimatter. If you drop a slice of toast, it does not produce anti-toast. If you misplace your keys, they do not annihilate with anti-keys in a burst of gamma rays. Human life is conducted at scales where antimatter is not part of ordinary experience, except in extremely specialized conditions. That is why its conceptual impact is so strong. It is not just another kind of particle. It is a reminder that the particle world is not built according to the habits of thought that govern furniture and errands. The connection to time becomes even more suggestive when we consider why the reinterpretation works at all. In quantum field theory, particles are excitations of underlying fields. They are not little hard pellets in the old-fashioned picture. The theory must account for relativistic behavior and quantum behavior at once. In doing so, it naturally produces solutions corresponding to antiparticles. Recasting those solutions as particles moving backward through time turns out to be mathematically economical and conceptually fruitful in some contexts. It is one of those moves in physics that feels almost like a trick until one realizes it is not a trick at all, but a sign that the old categories of matter, motion, and temporal direction were too limited. This is where the sensational phrasing about particles existing before they are created draws some of its energy. If an antiparticle can be described as matter moving backward through time, then perhaps, the dramatic imagination whispers, some particle events are really future things masquerading as present ones. Perhaps a particle is somehow arriving from its own annihilation. Perhaps the effect is preceding the cause after all. One can see how the story builds itself, but again, the careful answer is gentler and more precise. The backward-in-time description is not licensed to claim literal retroactive appearance in the ordinary sense. It is a formal equivalence inside the theory, not a direct observation of time travel. Still, one should not rush too quickly past the weirdness. A formal equivalence of that kind is already astonishing. It means that the mathematical language we use to describe reality treats some distinctions that feel absolute to us as transformable under deeper symmetries. What looks like a rigid line between forward and backward may be, at least in part, a feature of perspective and representation. The world is not saying that all temporal order is fake, but it may be saying that some of the structures beneath temporal order are more balanced than experience suggests. There is a useful physical process to keep in view here, and that is pair production. Under the right conditions, energy can produce a particle and its antiparticle together. This is not energy becoming matter in some vague inspirational poster sense. It is a concrete process constrained by conservation laws and specific interaction conditions. A photon near a suitable environment, for example, can under the right circumstances give rise to an electron and a positron. One becomes two. Energy becomes mass and motion, and a pair emerges. Seen in the reverse description, annihilation and pair production are related in a beautifully symmetric way. Matter and antimatter meet and vanish into radiation, or radiation contributes to the creation of matter and antimatter. The line between creation and destruction begins to look less like a one-way street, and more like two faces of the same process. This symmetry is one reason particle physics can sound like it is toying with causality when in fact it is often toying with representation. A process viewed one way looks like creation. Viewed another, under transformed conditions, it looks like annihilation. A line in a diagram can be read differently depending on the direction assigned. It is enough to unsettle the classical imagination. We want each event to come with a label that says what it is, once and for all. Nature seems more relaxed about such demands. The role of antimatter in experiments also reinforces this. When particle beams collide at high energies, matter and antimatter can appear as part of the debris. They are not mystical invaders from another temporal domain. They are lawful products of the available energy and interaction rules, but because some of them are short-lived, because they may decay almost at once, and because the theory describing them already carries this strange backward-in-time reinterpretation, they become natural magnets for paradox-flavoured language. The particle is produced and gone in an instant. its antiparticle counterpart can be treated in one formal sense as its time-reversed relative. The detector sees only traces and products. It does not take much for the phrase before it is created to start whispering from the edges of the story. There is also an emotional reason antimatter holds this grip on the imagination. It feels like a double, not just another object, but a counterpart. Human beings are endlessly susceptible to the uncanny power of doubles. Mirror selves, shadow versions, the familiar made strange by inversion. Antimatter taps directly into that instinctive unease. It looks like matter with a sign changed, a kind of opposite that is not evil or magical, merely lawful and lethal in contact with the ordinary world. Add time reversal language to that, and the whole thing starts sounding like a philosophical thriller written by an equation. Yet for all its strangeness, antimatter is not speculative in the way some exotic ideas remain speculative. We know it exists, we produce it, we study it. Positrons are used in positron emission tomography, where antimatter plays a role in medical imaging. Antiprotons can be made and trapped for experiments. Researchers compare matter and antimatter carefully, looking for tiny differences that might help explain one of the biggest mysteries in cosmology, namely why the universe seems to contain far more matter than antimatter. If the laws were perfectly symmetric in every relevant way, one might expect the early universe to have made matter and antimatter in equal amounts, leaving very little ordinary matter behind after annihilation, and yet here we are, stubbornly made of matter, asking impolite questions about the imbalance. That imbalance is one of the reasons antimatter is not just a conceptual curiosity. It may hold clues to why anything like us exists at all. If matter and antimatter had perfectly cancelled one another everywhere, there would be no stars, planets, biological history, or late-night speculation about causal order. The fact that some asymmetry must have tipped the scales makes antimatter central to the bigger story as well as the strangest one. And once again, time lurks nearby, because some of the relevant asymmetries involve violations of symmetries tied to temporal reversal. For now, though, it is enough to notice how antimatter destabilizes the old image of particles as simple little objects marching straightforwardly through time. In classical intuition, an object is just itself, moving from earlier to later. In relativistic quantum theory, identity is tangled with symmetry. A particle and its antiparticle can be transformed conceptually into one another under the right operations. A path in time can be redescribed. A process can be mirrored. The neatness of the old story gives way to something more flexible and more abstract. Not unreal, just less parochial. There is a temptation, when speaking about these things, either to overstate the paradox or to flatten it into harmlessness. Both are mistakes. If one says antimatter literally proves matter travels backward through time, one has wandered into fiction. If one says the backward in time language is merely poetic and means nothing at all, one misses the profound symmetry that made the interpretation powerful in the first place. The right position sits between those extremes. The mathematics genuinely permits this reinterpretation. It reflects something real about the structure of the theory. But translating that structure into ordinary causal language requires great care, because our intuition was not built for it. It may help to think of the backward in time idea not as a claim about what a laboratory observer sees, but as a clue about how nature is organized beneath appearances. Just as the Earth can be understood as moving around the Sun even though it feels to us as though the ground is still, antimatter can be understood through a formal relation to reverse temporal motion, even though no one sees a positron popping out of next week. The theory speaks a language more general than direct perception. It is not obliged to preserve our first impressions. All of this becomes particularly relevant in places like CERN, where the boundary between theory and evidence is constantly negotiated through particle traces and decay products. If a short-lived particle gives rise to matter and antimatter in some chain of events, the interpretation of that chain leans on the theoretical framework that includes these deep symmetries. The detector does not simply hand over a little card explaining what happened. Physicists must reconstruct the event using concepts that are already richer and stranger than common sense. Antimatter is one of the reasons that reconstruction can sound as though time itself has become part of the puzzle, and perhaps that is the most useful way to carry it forward. Antimatter does not show us clocks running backward in the everyday world. It shows us that the laws describing particles are compatible with a deeper symmetry, in which our ordinary distinction between a particle going forward and an antiparticle going forward can be related to opposite temporal directions in the formalism. That is enough to keep the paradox alive without letting it become nonsense. It means the world is not violating causality outright, but it is quietly revealing that what we call forward may not be as primitive a category as we once thought. Once that possibility is on the table, another question almost immediately follows. If some particles and antiparticles are already challenging our simple picture of persistence and temporal direction, what are we to make of particles so short-lived that they barely seem to exist at all before turning into something else? Because few examples sharpen that feeling more than the Higgs boson, which entered physics as a triumph of discovery, and almost at the same moment reminded everyone that some of the most important things in nature are known only through what they leave behind. There is a special kind of scientific object that behaves less like an object and more like a rumour that turns out, after immense effort, to be true. The Higgs boson belongs very much to that category. It is one of the most famous particles in modern physics, one of the most important, one of the most discussed, and yet it is also one of the least available to anything resembling ordinary intuition. You do not see a Higgs boson in the comfortable sense in which you imagine seeing a chair, a tree, or even a planet through a telescope. You do not produce one and then stare at it for a thoughtful minute while making notes. It appears, if the collision conditions are right, and then it is gone almost immediately, breaking apart into other particles so quickly that the phrase short-lived begins to feel embarrassingly inadequate. This is part of what gives the Higgs boson such an odd place in the public imagination. It is often spoken of as though it were a hidden treasure finally uncovered, the last missing piece of a great scientific machine, and in one sense that is true. Its discovery was a triumph. It confirmed a central part of the modern theory describing elementary particles and their interactions. It helped explain why certain particles have the masses they do. It was one of the great goals of the Large Hadron Collider, and when evidence strong enough finally arrived, it was rightly treated as a historic moment. But the strange thing is that this famous particle does not stay around long enough to greet its own announcement. By the time scientists know it was there, it has already vanished into products that must be reconstructed with extraordinary care. That is why the Higgs fits so naturally into this broader story about causes, effects, and the feeling that particle physics occasionally makes things arrive in the wrong order. The Higgs boson is not a particle that literally exists before it is created, but it is a particle so brief that human knowledge of it can only come after its disappearance. It enters the world as a possibility in a violent collision. It decays almost at once. Its descendants race through the detector. The detector records their traces. Analysts sift through the data. Statistical patterns emerge, and only then, after a vast chain of inference, do physicists say, with confidence, that yes, a Higgs boson must have been there. Existence and evidence no longer sit side by side. The event is over before understanding begins. There is something almost perverse about this from the perspective of common sense. We're used to the idea that important things are stable enough to be inspected. If I tell you I have discovered a new species of bird, you would quite reasonably expect the bird to remain bird-shaped for longer than a fraction of a whisper. If I announce a new chemical compound, you might hope it survives the announcement. The Higgs boson, by contrast, is important precisely because it reveals a field that is thought to fill all of space, and yet the particle itself is so fleeting that its presence must be inferred from wreckage. It is rather like claiming to have identified a rare guest not because anyone met them, but because their coat was found on a chair, the biscuits were gone, and several very specific footprints led nowhere. This is not an embarrassment for physics. It is normal at that scale. Many unstable particles are known through their decay products rather than prolonged direct encounter, but the Higgs draws special attention because it sits at the crossroads of several deep questions. It is tied to the mechanism by which certain fundamental particles acquire mass. It is an excitation of the Higgs field which is understood to permeate the universe, and it was predicted long before it was found, which means its eventual discovery carried the emotional weight of a long-awaited confirmation. That weight makes its ghostly behaviour all the more striking. One waits for decades to confirm the particle, and when it finally appears, it barely grants reality enough time to say hello. To make sense of this, it helps to distinguish between the Higgs field and the Higgs boson. The field is the deeper part of the story. Modern particle physics describes the world in terms of fields that fill space. What we call particles are excitations or quanta of those fields, localized expressions of something more fundamental and spread out. In that picture, the Higgs field is not a little object hidden somewhere behind things. It is part of the background structure of the universe. Certain particles interact with this field, and that interaction contributes to their mass. The Higgs boson is a ripple in that field, a particular excitation that can be produced under very energetic conditions. That distinction matters because it helps prevent a common misunderstanding. People sometimes imagine the Higgs boson as a tiny bead of mass that somehow gets sprinkled onto other particles, as if the universe were seasoning matter. But the real picture is subtler. The field is everywhere. The boson is a temporary excitation of that field. It is the detectable particle form associated with the field, not the entire mechanism packaged into a convenient pellet. So when CERN discovered the Higgs boson, it was not merely finding another item for the subatomic stamp collection. It was finding evidence that this field-based description of mass generation had real physical footing. And yet the boson itself is notoriously brief. Its lifetime is fantastically short, far less than a billionth of a second. So short, in fact, that describing it as short-lived can feel like calling a spark fleeting after it has already gone dark. The Higgs does not fly across the detector as a tidy stable particle in the way an electron might leave a more direct track. Instead, it decays almost instantly into other particles, and those are what the detectors actually record. 2 photons, perhaps, or pairs of other heavy particles that themselves decay in turn. Each possible decay route has its own likelihood, its own background noise, its own practical challenges for measurement. This is one of the quiet marvels of the discovery. Physicists were not waiting for the Higgs boson to pose obligingly in front of a camera. They were searching for statistical excesses in very specific decay channels. They knew that if enough collisions were produced, and if the detector systems were sensitive enough, and if the theoretical expectations were right, then the decays should leave a fingerprint in the data. Not a single dramatic event that anyone could point to and declare, there it is beyond all doubt, but a pattern, a bump above background, a clustering of events near the right mass, evidence accumulating until the alternative explanation that this was all just chance and ordinary background processes became overwhelmingly implausible. This is where the Higgs becomes a perfect example of how particle physics changes the very feel of existence. In ordinary life, for something to exist means more or less that it remains itself long enough to enter our experience in a stable way. It can be pointed at, handled, returned to, perhaps ignored. The Higgs boson laughs gently at that requirement and continues decaying. Its existence is not a matter of leisurely persistence. It is a matter of lawful appearance and predictable disappearance. It exists as an event more than a durable object, as a brief excitation with a characteristic mass and specific decay patterns. One could say that it does not refuse to exist exactly, but it certainly refuses to exist on terms familiar to the human nervous system, and because it vanishes so quickly, our knowledge of it always comes through consequences. This is not merely a practical inconvenience, it has philosophical consequences too. The Higgs pushes us to ask what kind of thing a particle really is. if its identity is inseparable from how it decays? Is it best thought of as a tiny object in the old billiard ball sense? Not really. Is it better thought of as a quantized excitation in a field, defined by the way it can be produced and the channels through which it transforms? Much more so. The Higgs does not sit there being itself in isolation. It is known through interaction, through transformation, through the pattern of what follows from its brief appearance. That has a bearing on our broader theme because it makes the old causal narrative less comfortable. We want to say that first the Higgs exists, then later we observe what it does. But in practice, the observation is of what it has already become. The particle is reconstructed from its aftermath. The detector records the descendants. Physicists infer the parent. If one were feeling careless, one might say the evidence arrives before the thing itself is known. And indeed, that sort of phrasing is one reason the public can be tempted toward more dramatic interpretations. It feels as though the effect is all we ever get, and the cause is a kind of ghost we name later. The effect is even sharper, because the Higgs was never just any unstable particle. It had been anticipated for decades. The theory describing the electroweak interaction, one of the foundational pieces of the Standard Model, needed a mechanism of spontaneous symmetry breaking, involving a field like the Higgs field. Without getting lost in the undergrowth of mathematical formalism, the essential point is that the world, as described by the theory, required something like this structure in order for certain particles to have mass while the equations remained internally consistent. The Higgs boson was the experimentally accessible sign that this field was real. So when it was finally found, it was as though physics had located the footprint of an idea that had been haunting the theory for half a century. And still, the thing itself was gone almost before it arrived. There is something wonderfully humbling in that. Human beings spent decades building the conceptual framework, the accelerator, the detectors, the analysis techniques, and the international collaborations needed to bring this particle to light. And the particle responded by decaying essentially on the spot. One imagines the universe saying, quite politely, "I will reveal this to you, but only if you are willing to become very good at reading traces." Reading traces, in fact, is what the entire discovery depended on. Different decay channels offered different advantages. Some were rarer but cleaner, meaning the background processes that could mimic them were less overwhelming. Others were more common but messier, with ordinary interactions producing similar-looking debris. Physicists had to compare real collision data with elaborate simulations and theoretical expectations, all while calibrating detectors and controlling for countless sources of noise. The final claim did not come from romance, it came from statistics. Beautiful, patient, painstaking statistics. This is worth emphasizing because the public often imagines scientific discoveries as crisp moments of direct revelation. Someone looks through a microscope, someone shouts, someone writes history. The discovery of the Higgs was more like a mountain gradually emerging from fog. Individual events alone were not enough. The significance came from accumulation, enough collisions, enough patterns, enough confidence that what appeared in the data really corresponded to a new particle with the right properties. In that sense, the Higgs boson was not simply found. It was disentangled from an ocean of background and uncertainty. The short lifetime of the Higgs also connects to a more subtle feature of quantum physics. Particles that live for very short times do not show up with perfectly sharp masses in the naive classical sense. Their extreme instability is associated with a spread, a natural blurring in the exact energy distribution of the events through which they are detected. One does not get an infinitely precise spike from a particle that barely exists. One gets a resonance, a characteristic shape. This again pushes us away from the old intuition of a particle as a tiny enduring lump with an exact fixed identity at every instant. The Higgs appears more like a resonance in the field, a brief structured event with a measurable profile. There is something important in that shift. If the particles at the heart of modern physics are not really little marbles but excitations, resonances and decays in underlying fields, then many of our inherited mental pictures begin to look provincial. We have been taking the furniture of ordinary life and trying to place it inside a realm where the basic entities behave more like processes than things. The Higgs boson is an especially clear demonstration of this. Its identity is bound up with a field. Its discovery is statistical. Its lifetime is vanishingly brief. Its presence is inferred from what it leaves behind. If one insisted on common sense criteria for what counts as existing, the Higgs would seem almost rude in its refusal to cooperate. And yet that refusal is exactly what makes it scientifically rich. It tells us that persistence is not the price of reality. Things can be real without being durable. Things can matter enormously without lasting. This is not merely a sentimental thought smuggled in through the side door. It is a hard lesson from particle physics. Some of the most important ingredients in nature do not wait around to be admired. They flash into being under the right conditions and vanish into transformations that reveal their existence only to those equipped to read them properly. In this way, the Higgs is a kind of ambassador from a deeper level of reality where time itself feels less friendly. Not because the Higgs runs backward through time or violates causality, but because it weakens the ordinary connection between existence and temporal persistence. If a particle can be real while living so briefly that only its products are seen, then our human habit of tying existence to stable duration begins to look less like a deep truth and more like a local preference. We like things that stay put. The Higgs reminds us that the universe is under no obligation to share that preference. It also complicates the emotional grammar of discovery. Normally, finding something suggests arrival, contact, possession. With the Higgs, finding it means becoming convinced that a certain short-lived event must have occurred, based on the statistical behavior of many outcomes. It is discovery at a distance, in time as well as in method. The object of interest is already gone. What remains is evidence, and from evidence comes inference. One could almost say that the Higgs is discovered in retrospect by design. That retrospective quality is why it fits so well into the larger story of seeming temporal oddities at CERN. If you wanted to speak recklessly, you could say that the Higgs appears only after it disappears, which is not correct in the literal physical sense but does capture something about how human knowledge of it is structured. We know it through decay. The proof comes after the vanishing. The cause is reconstructed from the effect. Once again, common sense is not overthrown, but it is being asked to accept that reality on this scale is accessible only through trails and echoes. There is also a kind of irony in the public name the Higgs once acquired, a nickname that has caused endless trouble and not a little eye-rolling among physicists. That nickname encouraged the idea that this particle was somehow more mystical than the rest, as though it were a singular master key to existence. In truth, the Higgs is important, but it is not a divine bead of matter, nor a magical answer to every deep question. It is a crucial piece of a specific theoretical structure. Its discovery confirmed a major mechanism. Its properties continue to be studied carefully, because even tiny deviations from expectations could hint at new physics. But part of maturing beyond the myth is understanding that its strangeness lies not in some supernatural role, but in the very normal quantum fact that truly fundamental things often refuse to behave like the solid objects of daily life. And the Higgs still has more to teach. Measuring its properties precisely remains a major task. How often does it decay in one way rather than another? Does it couple to other particles exactly as expected? Does it hide any subtle deviations that would point beyond the standard model? The story did not end with its discovery. In some respects, the discovery was only the beginning of a long effort to understand whether this famously brief particle is exactly the one the theory predicted, or whether it carries hints of a larger, stranger structure waiting in the dark beyond. That matters because the Higgs sits right at the border between what we know and what we suspect we do not yet know. The standard model is extraordinarily successful, but it is incomplete. It does not explain dark matter. It does not incorporate gravity in the same quantum framework. it does not fully account for why the universe contains more matter than antimatter. So even while the Higgs confirmed one major piece of the structure, it also sharpened the sense that there are further layers still concealed. A particle can be found and still remain mysterious. In that sense too, the Higgs almost refuses to exist in the simple closed way we might wish. It is present, confirmed, essential, and still pointing beyond itself. There is a quiet lesson in all this about the nature of evidence. The most important realities are not always the ones that sit still longest. Sometimes they are the ones whose effects are so consistent, so patterned, and so difficult to explain away that absence itself becomes a form of presence. The Higgs boson is absent by the time we know it, and yet the traces it leaves are enough to make that knowledge firm. It is a particle written in aftermath. And that idea prepares us very naturally for what comes next. Because once we accept that some particles are known through traces, through brief appearances, through descriptions that depend heavily on the underlying symmetries of the laws, we are ready to ask a deeper and more dangerous question. If the laws themselves were played backward, would they still make sense? Would the world at the most fundamental level care about the direction in which time is told? Or are some of its deepest rules far less committed to the arrow of ordinary experience than the human mind has always assumed? There is a particular kind of surprise that physics likes to spring on people, and it often begins with a very simple experiment in imagination. Picture an ordinary event. Two billiard balls collide on a table, one rolls in, taps the other, and both move away at neat, sensible angles. Nothing dramatic, nothing mysterious, just an everyday example of cause, effect, and motion behaving exactly as they should. Now, imagine filming that collision and playing the film backward. The balls still move along possible paths. They still collide in a way that seems mechanically acceptable. If you had never seen the original, you might not immediately know which version was forward and which was backward. The laws of motion, at least in that simplified, idealized situation, do not raise a protest. That little mental reversal is the doorway into time symmetry, and it leads somewhere genuinely unsettling. Because one of the deepest facts about physics is that many of its fundamental laws do not care very much whether you tell the story from past to future, or from future to past. Reverse the direction of time in the equations, and the form of the law can remain the same. The mathematics still works. The structure still holds. The world, at least at that level, does not immediately insist on one preferred direction. That is a difficult thing to sit with because it rubs directly against the grain of ordinary experience. Daily life feels saturated with irreversible processes. Tea cools, ice melts, toast burns, dust gathers, batteries lose courage, hair does what it likes after sleep. Everything around us seems to declare that time has a direction and means to keep it. So when physics calmly suggests that many of its deepest laws look just as respectable in reverse, the natural response is to look at the world and ask whether the equations have somehow become detached from reality. But they have not. The trick is that one must distinguish between the laws themselves and the particular histories they allow. That distinction is one of the most important in all of physics, and one of the least intuitive. A law may permit processes in either temporal direction without forcing the universe to realize both directions equally in ordinary life. The rule can be symmetric, even when the world we happen to inhabit is not. That sounds like a legal loophole, but it is really a clue about how the deep structure of nature differs from the patterns we encounter at human scale. Let us begin with the simplest version. In classical mechanics, if you know the positions and velocities of objects at one moment, the laws let you calculate how the system evolves. If you reverse the velocities in just the right way, the same laws let the system retrace its steps. In that narrow and ideal setting, there is no built-in arrow of time in the equations themselves. The law does not say that one sequence is allowed and the reversed one forbidden. It says both are mechanically acceptable. That is why the reversed film of the billiard balls can still look plausible. The equations are not embarrassed by it. Of course, real billiard balls on a real table are not perfect examples. There is friction. There is sound. There is heat. The cushions are not ideal. Someone is probably holding the cue in a way that suggests confidence without justification. In real life, small losses and disturbances build up. Reverse the actual event in every microscopic detail, including all the scattered heat and air movement and sound waves, and the law would still permit the reversal in principle. But arranging that exact reversal is absurdly impractical. The difficulty is not that the law forbids it. The difficulty is that the world has an astonishing talent for becoming complicated. That talent is what often creates the human sense of temporal direction. We do not live among idealized systems. We live among systems with countless particles, endless interactions, and a strong tendency to drift from tidy arrangements into untidy ones. A dropped glass shatters. The reverse process, shards leaping together from the floor into a whole glass, is not forbidden by the deepest microscopic laws in the same straightforward way many people assume. It is just fantastically unlikely, because it would require an outrageous level of coordinated motion among an enormous number of particles. The law is permissive, probability is not. This is the first major lesson of time symmetry. The everyday arrow of time is not always written directly into the most basic rules. Often it emerges from the kinds of state systems begin in, and the overwhelming statistical tendency for disorder to increase. That means our lived sense of irreversible time may be less a matter of strict microscopic prohibition, and more a matter of what is overwhelmingly likely in a universe like ours. Put differently, the laws can be symmetric even while the world is not. The script allows both directions, but the stage keeps favouring one. That idea becomes stranger, not simpler, when we move from ordinary mechanics into the quantum world. Quantum theory, too, contains forms of time symmetry in important places. If one reverses certain aspects of a process carefully and appropriately, the mathematical structure can remain valid. At that level, too, the laws often refuse to privilege forward over backward in the obvious emotional way we do. They are far less sentimental about sequence than human beings tend to be. We remember the past, anticipate the future, and attach meaning to progression. The equations mostly keep working and wait for us to catch up. This is one reason the phrase arrow of time needs to be handled carefully. There are several arrows one can talk about. There is the thermodynamic arrow, tied to the increase of entropy, and the drift from ordered states toward more probable disordered ones. There is the psychological arrow, the fact that we remember earlier events and not later ones. There is the causal arrow of ordinary life, where we habitually describe causes as preceding effects. And then there is the question of whether the fundamental laws themselves distinguish past from future. These are related questions, but they are not identical. Much confusion enters the subject when one arrow quietly borrows authority from another. The laws of physics can be time-symmetric in form, while our experience remains powerfully one-directional. That is not a contradiction. It simply means that the source of the directional feeling may not sit where common sense first places it. We tend to imagine a kind of invisible cosmic current carrying everything from yesterday to tomorrow. The deeper picture may be less like a current and more like a vast rulebook in which many moves are reversible, even though the particular game we are watching has begun in a very special state and is unfolding along a path that becomes ever harder to retrace. There is a useful way to feel this difference. Suppose you watch cream swirl into coffee. Forward, it looks normal. Backward, it looks ridiculous. The cream seems to gather itself out of the dark liquid with uncanny precision, restoring a clean separation that no breakfast table in history has ever enjoyed for long. So you conclude, reasonably enough, that time clearly has a direction, but the microscopic laws governing the molecules do not individually forbid the reversed motion. The trouble is coordination. There are vastly more disordered mixed arrangements than neatly separated ones. Once the cream is dispersed, the universe has many more ways to remain mixed than to reassemble the pristine starting state. The asymmetry you notice comes from the structure of possibilities not necessarily from a built-in one-way instruction stamped on every microscopic law. That distinction is one of the grand quiet shocks of modern physics. We're used to looking for necessity where probability may be doing the heavier lifting. We say the egg cannot unscramble. Physics says something subtler. It says the underlying laws do not treat the reverse process as a myth in the simple mechanical sense, but the number of microscopic configurations corresponding to the scrambled state is so overwhelmingly larger than those corresponding to the neat unbroken state that the reverse simply does not happen in any ordinary practical context. Human language rounds that down to impossible, because human language has errands to run. Time symmetry also forces us to think carefully about what it means to reverse time in the first place. It is not enough just to run a mental film backward and call it a day. Certain physical quantities must be transformed appropriately. Directions of motion reverse. Some other quantities may behave differently under time reversal depending on their nature. One must be precise. Physics is rarely impressed by hand-waving on this point, though it has seen plenty of it. Time reversal is an operation with rules, not a vague mood of backwardness. This matters because once the idea is made precise, one can ask a serious question. Does a given law or interaction remain unchanged under that operation? For many familiar laws, the answer is yes, at least in idealized or approximate form. For some deeper processes, as we will soon see, the answer is not perfectly yes. But before getting to those cracks, it is important to appreciate how remarkable the broad symmetry already is. Nature at its most basic level often seems indifferent to the temporal preference that dominates human life. The universe does not instinctively share our attachment to before and after as moral categories, and perhaps that is why time symmetry feels so unsettling in a different way than other scientific ideas. It does not merely tell us that reality contains strange things. It tells us that one of our most trusted intuitions, that the world itself must fundamentally know the direction of time as clearly as we do, may be overstated. The laws may be more balanced than experience suggests. The asymmetry may come later, through boundary conditions, statistical behaviour, and the special history of our universe. That is a subtler picture, but also a more unsettling one because it relocates the source of temporal direction away from where ordinary thought expects to find it. A film played backward can help here, but only to a point. Some reverse scenes look absurd at once, because they involve entropy decreasing in glaring ways. Smoke gathering itself neatly back into a cigarette would be a strong clue that something had gone terribly wrong with the projector or the cosmos. But some simple interactions look perfectly plausible reversed. Two particles collide and separate. A pendulum swings. Waves interfere. The deeper you go into the formal description, the more you find laws that do not by themselves insist on a preferred temporal order. The absurdity enters through the specific state of the system and the context in which it unfolds. This is why high-energy physics is so relevant to the story. At places like CERN, scientists are probing interactions closer to the level where the fundamental rules are exposed. The collisions are brief, clean by comparison with everyday macroscopic chaos, and described by theories built around symmetry principles. There, the question of whether a process looks the same under time reversal is not merely philosophical decoration. It is part of the structure of the theory and part of what experiments can test. Symmetry is not an afterthought in particle physics. It is one of its organizing instincts. Physicists use symmetry the way skilled cooks use salt, carefully, constantly, and with the quiet understanding that many dishes simply collapse without it. Among the most important symmetries are those involving charge, spatial inversion, and time reversal. One can ask what happens if a process is transformed by changing particles into antiparticles, or by reflecting space, or by reversing the direction of time. For a long time, it was tempting to imagine that nature would respect these symmetries very generally. The deeper the rule, the more elegant the symmetry seemed, and indeed, much of modern physics was built on that expectation. but nature has a habit of honouring elegance only until it does not. Still, before we get to those violations, one should feel the force of the symmetry itself. If the laws of a process remain valid when time is reversed, then the distinction between cause and effect at that microscopic level is less absolute than it feels in daily life. Not absent, not meaningless, but less built into the law itself. The equations allow a process and its time-reversed counterpart as peers. Our emotional sense that one is natural and the other perverse comes from the world of large systems, heat flow, memory, and irreversible mess. The particle world often has cooler manners. That cooler manner is part of what makes sensational claims about particles appearing before they are created sound almost plausible to the public. If many fundamental laws do not care about time direction, and if antiparticles can be formally related to backward temporal descriptions, and if unstable particles are known only through the evidence left by their decays, then the stage is set for dramatic misunderstandings. One begins to think that perhaps the microscopic world really does let effects come first. But time symmetry by itself does not say that. It says something subtler and, in its own way, more profound. It says that the laws may not privilege forward over backward at the fundamental level in the clean, simple way our everyday minds had assumed. The challenge, then, is to understand where the asymmetry we do observe actually enters. Part of the answer lies in entropy and statistical mechanics, as we touched on earlier, but another part lies deeper in particle physics itself, because not every symmetry is perfect. There are rare and precious cases where nature does seem to choose one-handedness over another, one orientation over its mirror, one temporal behaviour over its reversed counterpart. Those cracks matter enormously, because they hint at why the universe contains matter at all, instead of having cancelled itself into radiation long ago. They suggest that even if the laws are largely symmetric, the symmetry is not complete. This is where the story sharpens. Time symmetry is not just a grand philosophical possibility. It is something that can be tested, challenged, and in some contexts found wanting. The universe is not maximally biased toward a temporal direction in every law. But neither is it perfectly neutral in every interaction. There are tiny departures, minute preferences, subtle violations hiding in certain particle decays and transformations. And those small preferences may be among the reasons any solid matter exists for us to sit on while thinking about them. So the calm, broad statement is this: many fundamental laws of physics look the same in reverse, and that should permanently complicate any naive claim that the arrow of time is written directly and uniformly into the deepest layer of reality. But the universe is not finished with us there. Just when symmetry begins to sound almost too clean, certain processes involving matter and antimatter reveal that the balance is not exact. And once that door opens, we find ourselves in one of the most consequential and delicate parts of the story, where tiny violations of symmetry may explain why the cosmos ended up with stars, planets, tea, and listeners rather than a nearly perfect cancellation of everything into light. That is where CP violation enters, and with it one of the most quietly dramatic discoveries in modern physics. Quietly dramatic is perhaps the best phrase for it, because nothing about CP violation announces itself in the way people usually imagine great scientific revelations. There is no giant flash, no particle politely stopping to say it has broken one of our assumptions, no cosmic alarm bell going off somewhere over Geneva. Instead, there is a very small mismatch, a tiny preference, a minute asymmetry in the behaviour of matter and antimatter, and yet that tiny mismatch may be tied to one of the largest facts about existence, namely that the universe contains enough ordinary matter for stars, planets, oceans, trees, lungs, and sleepy discussions of particle physics to exist at all. To feel the force of that, it helps to begin with the symmetry itself. In particle physics, charge refers to the transformation that swaps a particle for its antiparticle. Positive becomes negative, matter becomes antimatter, and the relevant quantum properties change sign in the right way. Parity refers to a mirror flip in space, as though the entire setup were reflected left to right. If you combine those two operations, taking a process and replacing every particle with its antiparticle, while also mirror reflecting the whole arrangement, you get what physicists call CP. For a long time, there was strong reason to hope that nature would respect this combined symmetry, even if the separate pieces were not always preserved. That hope had already taken one blow earlier in the 20th century, when parity by itself turned out not to be sacred in weak interactions. This was a major shock. The idea that the laws of nature might care about left and right in certain processes seemed almost rude. It violated a kind of aesthetic expectation, the feeling that the universe should not have a preferred handedness. But once that was accepted, CP emerged as a possible rescue of sorts. Perhaps left and right alone were not enough. Perhaps matter and antimatter had to be mirrored as well. Then maybe the deeper balance would be restored. For a while, that looked plausible. The equations behaved. The theory remained elegant. The unsettling asymmetry and parity could be absorbed into a broader combined symmetry. There was something satisfying about that. It suggested that nature, though slightly mischievous, still possessed a more general fairness. A process run with antimatter in a mirror image of the original would behave the same. The world would still honour a deeper balance even if it had stopped being polite about left and right separately. Then came the kaons. Now, neutral kaons are not particles that ask for public affection. They are not intuitively charming. They do not sound like anything one ought to invite to dinner, but they turned out to be among the most revealing messengers in all of particle physics. A neutral kaon is a meson, a particle built from a quark and an antiquark. In this case, it comes in a neutral form and an anti-neutral form, and because of the strange workings of the weak interaction, these two can transform into one another. They mix, they oscillate. A particle prepared in one form can later be found in the other. Already that is an interesting business, a kind of identity wobble built into the particle world. The important thing is that this mixed system produces states with different lifetimes. Some decay quickly, others last a little longer, though still not by any standard a human being would call leisurely. Physicists studying these decays in the 1960s expected that if CP symmetry held, then the long-lived state should decay only into certain kinds of final products, and not into others. It was a clean expectation. The universe had been handed a simple instruction: be symmetric under the combined operation of charge swap and mirror reflection, and then the universe said, very quietly, no. In 1964, James Cronin and Val Fitch, along with their collaborators, found that the long-lived neutral kaon occasionally decayed into a state it should not have reached if CP symmetry were exact. The effect was small, that is important. It was not some grand, repeated theatrical breakdown. It was a slight leakage, a rare channel, a tiny imperfection, but it was enough. Once observed, the conclusion was unavoidable. CP symmetry was not exact. Matter and antimatter, even when mirrored properly in space, were not always perfect twins in their behaviour. It is hard to overstate how significant that was. A tiny asymmetry in a lab, involving particles most people had never heard of, had just told physics that one of its cherished symmetries was only approximate. Nature, at least in weak interactions, was making a distinction between matter and antimatter that could not be erased by simply flipping the whole setup in a mirror. This was not a matter of opinion or aesthetic disappointment. It was experimental fact. The world itself had tilted, however slightly, and slight is the key word here. CP violation is not a loud phenomenon in everyday life. Your kitchen does not reveal it. Your bicycle does not require corrections for it. Clouds do not drift in patterns that betray it. It lives in delicate particle processes, in rare decays, in precise experiments, in the sort of environment where physicists spend years building detectors and then celebrate by giving a phenomenon a name that sounds restrained almost to the point of comedy. Violation, as if the universe had merely parked in the wrong place. but that restraint hides the scale of the implication, because once you accept that matter and antimatter do not behave in perfectly matched ways, a door opens onto one of cosmology's deepest questions. Why is there so much matter in the universe at all? This is not a rhetorical puzzle, it is a genuine problem with teeth. The early universe, as we understand it, should have been hot enough and energetic enough to produce matter and antimatter in abundance. If those had remained in perfect balance and obeyed fully symmetric rules in all relevant respects, then as the universe cooled, most of the matter and antimatter would have annihilated each other. The result would have been a cosmos filled mainly with radiation, with very little leftover matter to build galaxies or anything more intimate. And yet clearly some matter remained. Not just a trace in an abstract sense, but enough to make everything familiar. So something must have tipped the scales. Somewhere in the deep early history of the universe, there had to be processes that treated matter and antimatter differently enough to leave a small excess of matter behind. Small is again the important word. The imbalance did not need to be huge, it only needed to be enough. If for every enormous crowd of annihilating particle-antiparticle pairs there was just a tiny surplus of matter, that tiny surplus would be what remained after the great mutual destruction finished its work. Everything solid, we know, would then be the residue of a very slight preference written into the laws. That is an extraordinary thought. It means the existence of ordinary matter may depend on nature not being perfectly fair. There is a famous set of conditions associated with this idea, laid out by the physicist Andrei Sakharov. If the universe is to generate a matter surplus dynamically from an initially more symmetric state, then certain ingredients are needed. There must be processes that allow the number associated with baryonic matter to change. There must be a departure from thermal equilibrium, so that the universe is not simply undoing every asymmetry as fast as it appears. And crucially, there must be violations of certain symmetries, including CP, so that matter and antimatter are not treated as exact equals. Without that last ingredient, there is no reason for one side to win even slightly. So when CP violation was discovered in kaons, it was not merely a technical curiosity, it was evidence that the universe possessed at least one of the ingredients needed to create a matter-dominated cosmos. The effect measured in the laboratory was tiny, but it pointed toward a possible answer to a giant question. It linked particle decays in controlled experiments to the broadest fact of cosmic history, the fact that the visible universe is not balanced evenly between matter and antimatter. Now, one must be careful here. The amount of CP violation built into the standard model of particle physics, at least in the forms we have measured so far, does not seem sufficient by itself to explain the entire matter excess in the universe. That's another one of those frustrating and fascinating situations where physics gives us part of the answer and simultaneously sharpens the mystery. We know CP violation exists. We know it is necessary in any plausible story of matter coming to dominate antimatter. But the observed sources may not be enough. There may be additional CP violating processes still hidden from us, perhaps involving particles or interactions not yet fully explored. The universe may be keeping some of its accounting methods private. That possibility is one reason experiments at CERN and elsewhere continue to study matter-antimatter asymmetries with such care. The more precisely we understand known sources of CP violation, the better we can judge whether the standard model is complete in this respect, or whether it is only giving us a small piece of a larger picture. Rare decays, heavy mesons, subtle oscillations all become clues. A tiny preference in one direction may point toward new particles, new interactions, or entirely new sectors of physics that helped shape the early universe. The standard model itself accommodates CP violation through the way quarks mix under the weak interaction. This is one of those statements that sounds modest until you unpack it. Quarks, the building blocks inside protons, neutrons, and many other particles, come in different types. The weak interaction does not always leave those types neatly isolated. It allows certain transitions among them, and the mathematical structure describing those transitions contains phases that can give rise to CP-violating effects. In plain language, the weak interaction carries within it a subtle mechanism by which matter and antimatter can behave differently in some processes. This is not easy to picture because it is not a matter of one particle simply deciding to misbehave. It is built into the interference of possible decay pathways, into the complex amplitudes that govern how likely different outcomes are, into the fine grain of quantum process. If you want a human scale analogy, it is less like someone choosing the left door over the right, and more like two nearly identical routes through a maze combining in such a way that one traveller gets a tiny statistical preference over their mirrored twin. The effect emerges from structure, not whim. The first discovery in kaons was only the beginning. Later experiments found CP violation in the decays of particles containing bottom quarks as well, especially certain neutral B mesons. These systems became major laboratories for studying symmetry with great precision. The beauty of these particles, if one may speak kindly of decaying mesons, is that they too can mix with their antiparticles and decay through multiple pathways. That makes them exquisitely sensitive to the same sort of subtle interference effects that allow CP violation to show itself. Large experiments were designed to track these decays in detail, measuring tiny differences between matter and antimatter behaviour and testing the predictions of the standard model again and again. This is the sort of work that rarely gets turned into a blockbuster trailer, but it is exactly where the real story lives. Thousands of events, careful calibrations, statistically significant deviations, cross-checks, detector upgrades, data analysis that would make most people quietly leave the room. And within that patient labour, a picture emerges. The universe is mostly symmetric in many respects, but not perfectly. It contains little cracks. Through those cracks, history may have flowed differently for matter and antimatter. There is something almost moral sounding about that, though it is not moral at all. We are tempted to say nature is biased, but bias implies preference in a personal sense. This is not personal, it is structural. The laws contain small terms and phases and interference patterns that do not cancel exactly under the combined CP transformation. Matter and antimatter are not enemies in a drama. They are participants in a rule set that does not treat them with complete equality. The resulting imbalance may be enough to explain why one side left more residue behind, and that residue is us. It is worth pausing there, because it is one of the most direct links between particle physics and lived reality. We often talk about fundamental physics as though it belongs in a sealed chamber far away from ordinary concerns, but the existence of CP violation means that tiny asymmetries in subatomic processes may be directly responsible for the existence of every solid thing you have ever touched. The chair beneath you, the pulse in your wrist, the page on the screen, all may owe their material existence to the fact that the laws were not exactly balanced between matter and antimatter. Perfect symmetry would have been elegant. It would also have been catastrophically empty. This also changes how one thinks about the word tiny. In ordinary life, tiny can sound dismissive. A tiny error in a recipe may be forgiven. A tiny stain can perhaps be ignored if the lighting is kind. A tiny delay is irritating but survivable. In cosmology, tiny can be decisive. The entire visible universe may hang on a mismatch so small that it only reveals itself in rare particle decays and painstaking statistical studies. There is a useful humility in that. Vast consequences do not always require large causes in the obvious sense. Sometimes a minute deviation, repeated across the furnace of the early universe, is enough to change everything. Now, because our broader theme concerns time as much as matter and antimatter, CP violation carries an additional charge. If the laws were perfectly symmetric under this combined operation, and also obeyed deeper theorems connecting the fundamental symmetries of physics, then time reversal would fit into the balance in a certain way. Once CP is violated, the the question of time reversal becomes more than a philosophical curiosity. The asymmetry between matter and antimatter begins to hint that the laws may not be perfectly neutral under time reversal either, at least in specific processes. The tiny imbalance that changed the universe may also be one of the places where the microscopic world reveals a real preference about temporal order. But before stepping fully into that, it is useful to hold on to the concrete picture. In laboratory experiments, neutral kaons and certain other mesons do not always decay the same way as their antimatter counterparts under mirror-reflected conditions. The difference is small but measurable. It is real, tested, repeated, and folded into the framework of modern particle physics. This effect points toward a broader cosmic asymmetry that may explain why matter survived. That is the clean version. It is already strange enough without embellishment, and yet the embellishment is understandable. Once you hear that the laws are almost symmetric but not quite, that matter and antimatter are almost mirrors but not exactly, that the universe may owe its material content to a tiny betrayal of balance, it is difficult not to feel that something deep and dramatic has happened, because it has. The important thing is that the drama is precise. It lives in branching ratios, oscillation patterns, rare decays, and interference effects. It does not need to borrow the language of fantasy. The real version is more than sufficient. There is also a pleasing reversal of scale here. Human beings often imagine the cosmos as being shaped by grand sweeping events and obvious overwhelming forces, and of course it is, in part. Supernovae, gravity, expansion, black holes all have their say. But the composition of the universe may also have been decided by an imbalance so delicate that only very careful particle experiments can bring it to light. The grandest stage and the finest detail are not opponents, they are partners. A smaller symmetry in the early furnace can echo outward into galaxies. That partnership is one of the reasons CERN matters so much in this story. It is not merely a place where particles are smashed for sport or for the pleasure of making headlines nervous. It is a place where the subtle bookkeeping of reality can be examined. If there are additional sources of asymmetry hiding in heavy particles or rare decays, if the standard model is only part of the explanation, then the detector halls and analysis rooms of high-energy physics are where those clues may emerge. The matter-filled universe we inhabit is, in a very real sense, an experimental question that has not yet been fully answered. So CP violation stands as both answer and provocation. It answers the old assumption that matter and antimatter must be perfect mirrors in all relevant respects. They are not. It answers the question of whether nature can break this combined symmetry. It can. But it also provokes larger questions. Is the known amount enough? Where else might a symmetry hide? What other processes in the early universe contributed to the imbalance? And perhaps most intriguingly for our purpose, what does this tiny preference imply about time itself at the deepest level? Because once symmetry is cracked here, it becomes possible to ask whether time's own mirror is also imperfect. And when experiments begin to probe that question directly, the story moves from the imbalance between matter and antimatter into something even more unsettling. The possibility that nature in certain processes truly does distinguish between forward and backward, not just in our thermodynamic everyday way, but in the core behaviour of its microscopic laws. Once CP symmetry has been found to fail, the next question almost asks itself. If matter and antimatter are not treated in perfectly mirrored ways, what does that mean for time reversal itself? After all, the language of symmetry in physics is not just decorative. These operations are related to one another in deep and tightly structured ways. So if one part of the balance is cracked, it becomes natural to wonder whether time's side of the arrangement is also under strain. That is where T-violation enters, and with it one of the most delicate and unsettling ideas in particle physics. Because this is the point in the story where one can no longer take shelter in the vague comfort that maybe the laws are entirely indifferent to temporal direction after all. In certain rare processes, nature seems to lean. That sentence needs to be handled with care. nature seems to lean does not mean clocks begin to run backward in the laboratory. It does not mean coffee leaps from cup to kettle or that tomorrow has been caught meddling with today. It means something more technical and, in its own way, more profound. It means that if you take certain microscopic processes and apply the proper time reversal operation to them, the reversed process does not occur with exactly the same behaviour or probability. The mirror is not perfect. The balance is not exact. There is, in that very precise sense, a difference between one temporal orientation and the other. For a long time, this was more a matter of implication than direct observation. Once CP violation had been discovered, many physicists were confident that some corresponding asymmetry involving time reversal must be present as well, provided another very deep principle called CPT symmetry remained intact. That principle is one of the great structural results of modern quantum field theory. In broad terms, it says that if you combine charge reversal, parity reversal, and time reversal all together, the laws should remain invariant under very general and powerful assumptions. It is one of the most respected pillars in the framework. So if CP symmetry is violated while CPT symmetry still holds, then time reversal symmetry must be violated in a corresponding way. The logic is elegant, the reasoning is firm, but there is a difference between a necessary inference and a direct measurement, and physicists, when they are being their best selves, care very much about that difference. So one of the great challenges was to observe T violation directly, not merely deduce it from the existence of CP violation and the trustworthiness of CPT. That is a much more difficult task than it may first sound. Reversing time in a deep physical sense is not the same as running a video backward. It is not enough to look at a decay process and imagine the final particles somehow reassembling into the initial one. In unstable systems, that kind of literal reversal is practically hopeless, because the exact reversed setup is not something one can arrange cleanly in the laboratory. The particles are too short-lived, the conditions too specific, the control too demanding. One needs a more subtle strategy. This is where particle physics, as it so often does, solved a conceptual problem by becoming more ingenious than ordinary intuition had expected. If you cannot directly force a decayed system to run backward like a rewound toy, perhaps you can identify pairs of transitions between quantum states that are genuine time reverses of each other and then compare their rates. That is the core of the method that eventually led to a direct observation of T violation in certain meson systems. It is not simple, it is not flashy, but it is beautiful in the way only carefully designed experiments can be beautiful, where the difficulty of the problem is met with a level of patience that almost becomes moral. The particles involved here are again the neutral mesons, especially those containing heavy quarks. These are deeply useful creatures if one is interested in subtle asymmetries, because they can oscillate between particle and antiparticle forms. A neutral B meson can evolve into its antiparticle and back again. Identity becomes a little fluid. The system lives in a space of states that can mix, evolve and decay in ways that are exquisitely sensitive to tiny differences. It is rather like having a set of clocks so delicate that they can reveal the warp in a flaw most people never knew was there. To understand why these mesons are so helpful, it is worth slowing down over the idea of oscillation. In ordinary life, identity feels stable. A chair remains a chair. A spoon does not spend the afternoon turning into anti-spoon and back. In the quantum world of neutral mesons, however, a particle prepared in one state can later be found in another related state because the underlying quantum evolution allows mixing. The particle and antiparticle are not isolated islands. They are connected through the weak interaction. Their behaviour over time depends on combinations of states with different properties, including slightly different masses and lifetimes. That already stretches common sense, and once such mixing exists, one can design experiments that compare transitions in one temporal direction with their time-reverse counterparts. The direct observation of T violation was achieved with extraordinary cleverness by looking at entangled pairs of B mesons produced together. Entanglement is one of those words that risks overuse because it has become so famous, but here it earns its keep. When two neutral beam mesons are created together in the right way, their quantum states are linked. Measuring or identifying the decay of one gives crucial information about the state of the other at that moment. This allows physicists to prepare and tag specific transitions indirectly, and that in turn makes it possible to compare pairs of processes related by time reversal. The logic of the measurement is subtle enough that it deserves a gentle example in spirit, even if not every technical detail can be unfolded without turning the evening into a graduate seminar with very poor lighting. Imagine that one can identify one class of state by the way it decays into a certain final product, and another class of state by a different signature. By using the entangled partner as a tag, one can determine that a meson started in one effective state and later ended in another. Then one can compare that transition with the reverse transition, where the starting and ending states are exchanged in the way required by time reversal. If time reversal symmetry held exactly, the rates of these paired transitions would match. They did not. This was a remarkable result, because it turned the idea of T-violation from a beautifully reasoned inference into a directly observed feature of the world. Not a metaphor, not a secondary conclusion, not merely the shadow cast by CP violation, but something seen in the behaviour of the meson system itself. The significance was not that time had been defeated or that the universe had abandoned order. The significance was that the laws governing certain microscopic transitions are not perfectly neutral between temporal opposites. In those rare processes, the same exact indifference that we once imagined at the deepest level is simply not there. It is worth pausing over how extraordinary that is, without exaggerating what it means. The ordinary arrow of time that governs daily experience is still dominated by thermodynamics, by entropy, by the immense statistical drift from order to disorder. T-violation in particle physics does not explain why milk mixes into coffee, or why dust gathers, or why memory points toward the past. Those features of temporal direction belong to another level of description. But T-violation does mean that at the level of certain fundamental interactions, the laws themselves are not perfectly symmetric under time reversal. That is different and in some ways deeper kind of asymmetry. The universe does not merely look one way because of initial conditions and statistics. In rare corners of its microscopic behaviour, it actually distinguishes. That distinction is easy to over-dramatise if one is not careful. One might hear that time reversal symmetry is violated and conclude that this is proof of effects preceding causes. But that is not the right lesson. T-violation is not a license for paradox. It does not mean that future events are out roaming the countryside influencing their own origins in ordinary circumstances. What it means is that if you compare a process with the corresponding time-reverse process, they are not always treated equally by the weak interaction. The laws are slightly lopsided. That lopsidedness matters for deep theory and cosmic history, but it does not open a little door to cinematic retrocausality. Still, one can see why the language of temporal oddity becomes tempting here. If time's perfect mirror is cracked, then perhaps the old confidence in neat forward order begins to feel less secure. Add to that the formal time-reversed descriptions in quantum theory, the strange role of antimatter, the fleeting nature of particles like the Higgs boson, and the indirect way events are reconstructed from their aftermath, and suddenly the headline writers are already halfway to saying that CERN may have found something that arrives before it is made. They are wrong in the literal sense, but they are not reaching into complete fantasy. They are reaching clumsily toward a real tension in the underlying physics. The crack in the mirror also has a philosophical weight that is hard to ignore. For centuries, one could imagine that temporal direction in the deepest laws was an illusion of scale, a byproduct of entropy and memory, while the microscopic world itself remained beautifully unbiased. T-violation forces a refinement of that picture. The microscopic world is mostly very symmetric in many respects, yes, but not perfectly. There are exceptional processes where the rulebook itself prefers one temporal orientation over the other. That does not restore ordinary common sense, but neither does it leave us in a universe of complete temporal neutrality. The truth is more uneven, more selective, less tidy. This selectivity is part of what makes particle physics so difficult to translate into broad public understanding. The asymmetry is real, but tiny, important, but highly specialized, deep but not visible in the ordinary motion of familiar objects. It would be far easier from a storytelling perspective if time reversal symmetry were either perfectly sacred or explosively broken in every corner of life. Instead, the universe gives us something more subtle. It honors the symmetry widely, then breaks it quietly in certain weak interactions among unstable particles most people will never meet outside a diagram. The cosmos has a taste for understatement in its most consequential gestures, and consequential they are, because T-violation sits in intimate relation to the same broader asymmetries that may have allowed matter to survive over antimatter. If the laws had been perfectly impartial in all relevant ways, the early universe would have had a much harder time leaving behind the slight surplus of matter from which everything visible is made. The direct observation that time reversal symmetry is violated in some particle transitions reinforces the broader lesson that the universe is not governed by complete balance. It contains biases, minute but real, and those biases may have shaped history on the largest possible scale. It is important, though, not to pretend that the known T-violating effects by themselves solve all the cosmic puzzles. Just as the known sources of CP violation in the Standard Model do not seem sufficient on their own to explain the full matter-antimatter imbalance, the measured T-violating phenomena are part of the story, not its completion. They tell us that temporal symmetry can fail directly. They confirm a deep structural feature of the weak interaction. They sharpen our sense that the laws are not perfectly mirrored, but they also point toward the likelihood that more remains hidden. If the observed asymmetries are too small to account for the visible universe in full, then there may be additional sources of violation yet undiscovered, perhaps in neutrino physics, perhaps in heavier particles, perhaps in sectors of reality we have not yet probed clearly enough. That unfinished quality is worth savouring, because it means the crack in time's mirror is not only a conclusion, it is a clue. It tells us where the symmetry fails, but not necessarily all the ways it may fail. It gives a foothold, not a final map. And that is often how progress in physics really works. One rare process refuses to behave symmetrically. A detector notices. A collaboration checks and rechecks. A result becomes credible. Then the real trouble begins, because now the theory must explain not just the existence of the effect, but its size, its origin, and its role in the larger architecture of the universe. There is also a human temptation here to confuse the violation of time reversal symmetry with the violation of time itself. That confusion is understandable, but it should be resisted. Time as we live, it remains a broad, layered phenomenon. The psychological direction of memory, the thermodynamic drift toward higher entropy, the cosmological expansion of the universe, and the microscopic asymmetries in weak interactions are related threads, but they are not all the same thread. T-violation does not mean your future self can send your present self a useful shopping list. It means that certain subatomic transitions are not indifferent to reversal under the formal operation that physics defines as time reversal. That is enough to be astonishing without turning it into prophecy. Yet the emotional effect of the discovery is undeniable. It changes the mood of the subject. Before, one might have said that the deepest laws look time-blind, and the arrow arises only later from large-scale conditions. After T-violation, one must say something more nuanced. Most of the laws are remarkably balanced in many contexts, but there are genuine microscopic asymmetries in how time-reversed processes behave. The universe is not wholly indifferent. It has small preferences. Those preferences are rare, and they do not govern daily life in the obvious way, but they are real. That alone is enough to alter the philosophical landscape. In a curious way, this makes the world both stranger and more grounded. Stranger because the neat dream of universal temporal symmetry has been spoiled. More grounded because the asymmetry is not vague or mystical. It is measured. It appears in specific systems, specific transitions, specific decay patterns. It lives in data. The universe is not offering us an interpretive mood. It is offering a result. One can admire that. If nature is going to disturb our assumptions, there is something reassuring in the fact that it does so with statistical significance rather than dramatic monologue. This measured disturbance also helps clarify what is and is not at stake in the claim that a particle may seem to exist before it is created. T-violation does not prove any such literal thing, but it does undermine the simplistic belief that time reversal is always an exact symmetry of the laws. It tells us that the forward and backward versions of certain microscopic processes are not perfect twins. That means our old assumption that temporal order is purely a matter of large-scale thermodynamic accident is incomplete. Some asymmetry is written into the interactions themselves. Once that is true, even a little, the door is open for the language of temporal peculiarity to creep back into descriptions of exotic particle behaviour, and that is where the story now has to become more careful than ever. Because after all this symmetry and violation and backward in time language, it becomes essential to answer the central question plainly. If CERN studies processes where causality can seem slippery, where antimatter invites time-reversed descriptions, where unstable particles are known only after they decay, and where even time reversal symmetry itself is not exact, then what are we actually justified in saying? Did CERN really find a particle before it was created? Or are we standing, as is so often the case in modern physics, in that difficult and fascinating space where a sensational sentence points toward a real mystery, but still overshoots the truth? So now we can finally ask the question in plain language and answer it without blinking. Did CERN really find a particle before it was created? No, not in the literal sense. Not in the sense that would make your kettle boil before you switched it on, or your train arrive before it left the station, or your shopping list write itself out of pity for your future. CERN has not produced direct evidence that a particle simply exists ahead of its own creation in ordinary chronological time. No experiment has shown a clean, usable reversal of cause and effect in the everyday sense people mean when they hear a claim like that. No physicist at CERN has had to pause a meeting because tomorrow wandered into the detector hall. And yet it is not hard to see why the question keeps returning, because the real physics around it is strange in exactly the right way to invite that kind of headline. It lives in the gap between what the public means by a particle and what particle physics actually studies. It lives in the gap between direct observation and reconstruction, between classical stories and quantum descriptions, between the ordinary flow of time and the deeper symmetries that do not always treat that flow as sacred. The dramatic claim is wrong, but the tension it gestures toward is real. The cleanest way to put it is this: CERN has found, studied, and helped clarify processes in which the order of explanation becomes less comfortable than the order of events. That is not the same as reversing causality, but it is enough to make a simple story start to wobble. The collisions happen first. The unstable particles are produced first. Their decays happen next. The detector records the aftermath after that. Then physicists reconstruct what must have happened. So the knowledge of the cause arrives through the effect. The particle, especially if it is short-lived, may already be gone by the time the evidence that identifies it has reached human understanding in a meaningful form. That is an important distinction, because it is one of the main engines of confusion. If a particle is known only through what it decays into, then the practical story of discovery begins with the effect. One sees the daughters, the traces, the energy deposits, the event shapes, and from those one infers the parent. The parent is not appearing before it is created. The parent is being known after it has vanished. That may sound like a minor correction, but it changes everything. The paradox shifts from physics to epistemology, from what happened in the collision to how humans come to know what happened in the collision. The Higgs boson is a perfect example. It does not sit around long enough to be examined like a specimen. It appears in a high-energy event and then decays almost instantly into other particles. Those secondary particles are what the detector actually records. Physicists then reconstruct the event and say, based on the pattern of outcomes, that a Higgs boson must have been produced. If one wanted to be irresponsible with language, one could say the evidence for the Higgs showed up after the Higgs had already ceased to exist, and from there it is only a short and regrettable walk to saying something like, it was detected before it was created. But that is not what happened. What happened is more disciplined and more interesting. The event occurred in the right physical order. It is our access to the event that came through the ruins. There is another way the misleading idea gets traction, and that comes from quantum theory itself. As we've already seen, some experiments allow later measurement choices to seem strangely tied to what we can say about earlier events. Delayed choice setups and quantum eraser experiments are especially fertile ground for confusion because they tempt us to narrate the situation in classical language and then act shocked when the language collapses. We say the particle must already have decided which route it took. Then the later measurement seems to alter what that earlier route could have meant, and suddenly it sounds as if the future is leaning back on the past. But many physicists would say the real lesson is not that the future changed the past. The lesson is that the past was never properly describable in the neat classical way we tried to impose on it, before the full measurement context was specified. That distinction is annoyingly subtle, which is one reason sensational headlines thrive. They do not enjoy distinctions. They prefer a clean, dramatic shape. Particle exists before creation is a much easier sentence to sell than the later measurement context constraints which classical description can meaningfully be assigned to the prior quantum system. One of those sentences sounds like a revelation. The other sounds like the beginning of a very serious headache, and yet the headache is closer to the truth. Antimatter contributes its own share to the confusion. In some formal descriptions, an antiparticle can be treated as a particle moving backward through time. That sentence is famous because it is both mathematically meaningful and publicly hazardous. What it does not mean is that CERN has watched antimatter literally travel into the past in a way that overturns ordinary chronology. What it does mean is that the equations of relativistic quantum theory allow a deep symmetry under which those descriptions are related. It is a statement about formal structure, not a video recording of tomorrow arriving early. But once that phrase enters circulation, it naturally encourages the idea that particle physics has found tiny loopholes in time itself. Again, the literal claim is too strong. The suggestive mood, however, comes from real theoretical ground. Then we arrive at time symmetry and its failures. Many fundamental laws look the same when appropriately reversed in time. That alone makes people uneasy, because it weakens the simple assumption that the deepest level of reality must care about temporal direction in the same way daily life does. But then nature complicates matters further by violating that symmetry in certain weak interactions. CP symmetry is not exact. T symmetry is not exact in all relevant processes either. The microscopic world is not perfectly balanced. So now the public hears that some laws do not care about time direction, while others slightly prefer one direction over another, and it becomes almost inevitable that someone will ask whether cause and effect themselves have begun to fray. But here too, the right answer is more careful than the dramatic one. T-violation does not mean that a final event can simply precede its own cause, in the everyday usable sense. It means that certain transitions and their time-reversed counterparts do not occur with perfectly matched behaviour. The laws are subtly asymmetric, that is important. It may be tied to why matter survived over antimatter. It matters profoundly for our understanding of the universe. But it does not amount to a demonstration that particles exist before they are produced. There is also a technical confusion buried in the word particle itself. Outside physics, the word suggests a tiny thing, A minuscule object with a stable little identity that pops into being, persists for a while, and then perhaps goes away. In modern particle physics, that picture is often too crude. Many particles are better understood as excitations of fields, resonances, unstable intermediate states, or quantum processes defined as much by their interactions and decays as by any durable object like persistence. So when people hear that a particle was present only briefly, or known only through its products, or represented in a calculation by an internal line that is not directly observable, they sometimes imagine that the particle was only half real, or retroactively real, or somehow suspended between existing and not existing in a way that invites dramatic language about time. But the more sober view is that particle physics has simply outgrown the old image of tiny marbles flying around. What exists at that level is not always a neat object in the common sense way. Sometimes it is an allowed excitation, with a certain mass range and characteristic decay channels. Sometimes it is a virtual contribution inside a calculation rather than a free particle one could detect directly. Sometimes it is a mixed state whose identity shifts over time. None of that requires the particle to predate its own creation. It requires us to refine what we mean by being a particle at all. This matters especially in collider physics because a great many interesting events are not observed directly from start to finish. They are reconstructed from products. A heavy unstable particle may be produced in a collision and decay before travelling any appreciable distance. The detector records the decay products. Their energies, directions, charges and timings are analysed. Missing energy may hint at invisible particles escaping. Statistical patterns over many events build confidence that the same parent process is recurring. In everyday speech, one might be tempted to say the particle appeared only after the evidence was assembled. In scientific speech, one says that the particle was inferred from the observed decay signatures. The order of physical events remains ordinary. The order of human certainty does not. That difference between physical order and epistemic order may be the single most useful key to the whole question. In physical order, the cause comes first. The collision produces the unstable state. The unstable state decays. The decay products strike the detector. Signals are recorded. In epistemic order, the detector signal comes first to us, then the analysis, then the interpretation, then the particle earns a name in the event record. One order belongs to nature, the other belongs to knowledge. Confusing the two is how headlines become paradoxes. Still, it would be too easy to stop there and say the whole issue is merely bad wording. It is not merely bad wording. The reason bad wording works so well here is that the underlying physics really does loosen some of the classical habits we rely on. Quantum theory does make measurement context unusually important. Antimatter really can be given that backward in time-formal description. Time reversal symmetry is not exact in all processes. Some particles really do exist for such brief spans that their reality is inseparable from the patterns they leave behind. All of that means the familiar sentence first, this happened, then that happened, in the exact clean way common sense prefers, is not always the most faithful language for what the theory is doing. So the honest answer has two parts. First, no. CERN did not find literal proof that a particle exists before it is created. Second, CERN absolutely does study a world where the ordinary language of before and after becomes strained. That strain is what people are dimly sensing when they latch onto paradoxical phrasing. They are misdescribing the science, but they are misdescribing something real. It may help to compare this with astronomy. Suppose you look at a distant star and say you're seeing the star as it was in the past, because its light took time to reach you. That sounds slightly mystical if one is not used to it, but it is simply how light travel works. You're not seeing the star before it existed. You're seeing delayed information about an earlier state. Something similar happens in particle physics, though on incomparably smaller scales, and with more reconstruction involved. You're not witnessing an effect that appears before its cause. You're gathering information whose meaning depends on what already happened and is now gone. The difference is that in astronomy, the delay feels intuitive once explained. In particle physics, the delay is tangled with unstable lifetimes, quantum descriptions, inference from decays, and sometimes the very structure of the theory. That makes it much easier for the language to slide into apparent temporal paradox. There is also a temptation to import more from philosophy than the physics can carry. If a later measurement seems relevant to how an earlier event is described, some people immediately want to declare that the future causes the past. If an antiparticle can be drawn as a particle moving backward through time in a diagram, some people want to conclude that time travel has been found in miniature. If T-symmetry is violated, some people want to say the universe has admitted that time itself is fundamentally broken. Each of these takes a real subtlety and pushes it one step too far. The real science is already strange, but it is a disciplined strangeness. It does not excuse every dramatic conclusion the imagination would prefer. Perhaps the clearest way to settle the matter is to ask what actual evidence would be needed to show that a particle existed before it was created in the everyday sense. One would need a robust demonstration that a future event can generate measurable present effects in a controllable causal chain that violates ordinary chronology and cannot be reinterpreted as delayed information, reconstruction, correlation, or formal symmetry. That is not what CERN has shown. Nothing in the established particle physics evidence requires that conclusion. Nothing in the successful predictions of the Standard Model depends on that conclusion. Nothing in the observed behaviour of Higgs bosons, meson oscillations, antimatter production, or CP&T violation amounts to that kind of literal reversed causation. But what the evidence does show is almost better, because it is more intellectually durable. It shows that ordinary common sense about time is not the whole story. It shows that the smallest events do not always come packaged in the classical narrative language we prefer. It shows that physical law can be more symmetric, more abstract, and more selective in its asymmetries than daily life suggests. It shows that causes can be known only through their consequences. It shows that the world is under no obligation to let our intuitions formed among chairs and kettles rule over quarks and bosons. And that is why the answer no does not feel disappointing, it feels clarifying. No, CERN did not find a particle lounging about before its own birth certificate was signed. But yes, CERN did help reveal a world in which the relation between event, evidence, measurement, and time is far subtler than common sense ever promised. The sensational version mistakes the shape of the mystery, not the fact that there is one. In some ways, that makes the true story more interesting than the false one. Literal time travel would almost be simpler. It would give us a familiar narrative shock and then leave the rest to engineers and lawyers. The real situation is harder. It asks us to accept that reality can remain causal, in the broad operational sense, while still resisting our preferred way of narrating causality. It asks us to distinguish between what the detector records and what the theory says. It asks us to live with symmetries that hold widely and violations that appear rarely. It asks us to treat particles not as miniature pebbles but as field excitations, resonances, decays and probabilities. That is less cinematic, certainly, but it is far richer. And perhaps that is where the question becomes most human. Why do we find these stories about backward particles so irresistible in the first place? Perhaps because time is not just another scientific topic. It is the medium of our lives. We live inside sequence. We regret backward and hope forward. We count, wait, remember, anticipate. So when physics hints that sequence itself may be less absolute than it seems, we do not hear that as a technical update. We hear it as a challenge to the basic furniture of experience. That is why these ideas echo so loudly outside the lab. So no, the particle did not exist before it was created. But the fact that the question can be asked at all, with even a shadow of seriousness, tells us something important. It tells us that modern physics has carried us to a place where the old assurances about time, identity and causality no longer fit without adjustment. The universe has not become incoherent. It has become more subtle. And once one sees that, the final question is no longer whether CERN found a particle before it was created, but what it means for us to inhabit a reality where that kind of sentence can sound almost plausible, and where the truth, though calmer, is in some ways more unsettling than the headline ever was. By now, the dramatic version of the story has had its turn. We have followed the claim, tested its edges, and watched it shrink into something narrower but more interesting. CERN did not uncover a particle lounging about before it was created. The future did not slip into the detector and start tampering with the event record. No one has caught cause and effect swapping seats in a way that would let us send messages backward, repair old mistakes, or finally arrive on time by exploiting a loophole in reality. The paradox in its loudest form is false, and yet the quieter version has only become stranger as we moved through it. Because what began as a sensational question turned out to point towards several real features of modern physics, each unsettling in its own way. Quantum theory does not always let us assign tidy classical histories in advance. Antimatter can be described in a formal way that makes time itself seem less rigid than common sense assumes. The Higgs boson and other unstable particles are known through what they leave behind rather than through direct durable presence. CP violation and time reversal violation tell us that the microscopic laws are not perfectly balanced after all. So the paradox was wrong, but it was wrong in an interesting direction. It reached too far, yet it reached towards something real. That, perhaps, is what the story really means for time. Not that time is an illusion in the cheap slogan sense, not that clocks are meaningless, not that chronology is dissolved, but that our ordinary understanding of time is local and practical rather than final. It is the understanding of creatures who live at one scale, for a modest span, among warm objects, flowing liquids, growing bodies, and persistent memories. At that scale, time behaves very well. It moves in one direction. Causes precede effects. The past feels fixed and the future feels open. A day lost to errands is still lost in the normal direction. There is nothing foolish about trusting that structure. It is how life works where we actually live. But physics is under no obligation to stop at the scale where our intuitions were trained. Once it descends into the subatomic world, the clear lines begin to soften. Events become processes, objects become excitations, identities mix. The distinction between what happened and what can be said to have happened under a certain measurement context becomes less obvious. Temporal symmetry, which daily life seems to deny at every turn, reappears in the laws more often than expected, only to fail in delicate special cases. The human picture of time as a simple one-way flow is not exactly wrong. It is incomplete. It is a reliable local map drawn without knowledge of the deeper terrain. There is something humbling in that. Human beings are extremely good at mistaking practicality for final truth. If a concept works in farming, cooking, building, storytelling, navigation, and family life, we naturally start to think it must also be the deepest available version of reality. Why would we not? It serves us well. But science has repeatedly shown that usefulness at one scale does not guarantee finality at another. Solid objects are mostly empty space at the atomic level. Straight lines curve in gravity. Stillness becomes relative. Heat becomes motion. Colour becomes wavelength and perception. Time, it now seems, belongs on that list. The version that governs human life is real enough to live by and still not be the last word. That matters for reality as well, because this whole story has quietly been forcing a broader question. What kind of thing is the world if some of its most basic ingredients are only known through traces, if some of its deepest laws nearly reverse without complaint, and if the asymmetries that shape cosmic history are so small that they hide inside rare particle decays? The answer, or at least the beginning of one, is that reality is not built for intuitive inspection. It is not arranged to be obvious. It does not present itself first in the conceptual forms that feel easiest to us. Instead, it yields itself through layers. Daily life gives one layer, engineering gives another, classical physics gives another. Quantum theory and particle physics go further still. Each layer is real, but none grants complete authority over all the others. This can feel unsettling because human beings like a world that fits into one story. We want one vocabulary that scales cleanly from toast to stars. We want one reassuring picture in which tiny things behave like little versions of larger things, and deeper knowledge only adds detail rather than changing the frame. Modern physics has been exceptionally rude to that wish. It has shown us again and again that the deeper picture often requires different concepts altogether. Probability is not just ignorance. Particles are not just miniature marbles. Empty space is not empty. Symmetry can be hidden, broken, or only approximately true. And time itself, the stage on which we place everything else, may be less like a river than our habits of thought suggest. Still, it is worth resisting the opposite mistake as well, which is to treat all of this as proof that reality is merely chaos wrapped in equations. It is not. If anything, the most striking thing about the story is how disciplined the strangeness is. The Higgs boson is not vague, its properties are measured. CP violation is not a mood, it is quantified. T violation is not a philosophical rumour. It is observed in specific transitions. The strange features of quantum experiments are not anarchic. They follow tightly constrained patterns. The universe is weird in a lawful way. That is one of the reasons these subjects are so compelling. They do not replace order with mystery. They reveal a kind of order that is richer than our first guesses. And that brings us to us, because there is always a temptation when discussing these deep questions to pretend that the human part is an optional afterthought. It is not. The whole subject lands so powerfully because time is not just a scientific variable to us. It is the medium of our personal lives. We feel it pass. We measure ourselves against it. We fear losing it. We wish for more of it. We regret what happened inside it and hope for what may still happen later within it. So when physics asks whether time is as simple as it seems, it is not merely shifting an abstract concept. It is touching one of the structures through which we interpret almost everything else. That is why stories about retrocausality or particles arriving too soon immediately take hold in the imagination. They hint, however inaccurately, that the framework of ordinary life might be negotiable. Perhaps the future is not as sealed off from the present as it seems. Perhaps effects can lean on causes. Perhaps time can be cheated. There is a very human hunger in those hopes, even when they wear the costume of scientific curiosity. We are creatures who remember and anticipate. Of course, we're drawn to anything that suggests the line between those acts may not be absolute. But the real lesson of physics is less generous to fantasy and more generous to understanding. It does not tell us we can rewrite yesterday. It tells us that the world is not required to mirror our preferred narrative forms. The future may not reach back in the useful dramatic way stories promise, but the structure of quantum description can still make later conditions matter to how earlier events are characterized. Antimatter may not be a fleet of tiny time travelers in the cinematic sense, but its formal relation to temporal reversal still tells us something deep about the symmetry of the laws. T violation may not let us send warnings to our younger selves, but it still proves that the microscopic world is not perfectly indifferent to temporal reversal. The universe does not grant the fantasy, but it does grant the difficulty. There is also a lesson here about language, and perhaps it is one science has had to learn the hard way. Human language evolved to coordinate ordinary life. It is wonderfully good at pointing to things like storms, hunger, doors, berries, promises, and suspicious noises in the dark. It is much less naturally equipped for describing entangled meson states, or resonances in quantum fields. So when strange physics reaches public discussion, our words strain. We borrow from ordinary intuition, and that can be helpful for a moment, but eventually the borrowed language starts to mislead. Before and after, object, path, cause, effect, even existence itself, all become trickier than their daily use suggests. The paradoxical headlines are one symptom of that strain. They are what happens when ordinary words are made to carry extraordinary concepts farther than they can comfortably go. Still, One should not be too hard on the impulse behind those headlines. Misleading as they can be, they often reveal where the real pressure points are. People do not latch onto these stories because they are irrational. They latch onto them because the deeper science really does challenge basic assumptions. If time can be treated symmetrically in some laws and asymmetrically in others, if matter and antimatter are almost mirrors but not quite, if particles can be reconstructed only from their decays, then the neat clockwork picture of reality begins to look provincial. The exaggeration is a misunderstanding, yes, but it is also a sign that people can feel the ground shifting underneath ordinary certainty. And perhaps that is the most valuable thing this paradox can do, once the exaggeration is removed. It can remind us that physics is not just a catalogue of facts about tiny things. It is an ongoing correction to the categories through which human beings understand the world. We often imagine discovery as adding new items to a shelf. Another planet, another particle, another force. Sometimes it works that way. But some discoveries do something deeper. They reshape the shelf itself. They alter what counts as a thing, as a process, as a cause, as a measurement, as a direction. Time belongs very much to that second kind of discovery. The more closely we examine it, the less it behaves like the simple container we once assumed. There is a quiet comfort in that too, though perhaps not the sort of comfort people usually seek from paradox. A world that is subtler than our first impressions is also a world that remains worth exploring. If everything had turned out exactly as common sense expected, then science would be mostly bookkeeping by now. Instead, even the most basic features of reality still carry layers we are trying to understand. Why does the universe favour matter over antimatter as much as it does? Are there hidden sources of CP violation still unmeasured? Is the standard model complete in this respect, or only a partial glimpse? How should we interpret quantum events when classical narratives fail? Does time emerge from something deeper, or is it fundamental in a form we still have not grasped clearly enough? These are not decorative questions. They sit close to the structure of existence, and if one steps back from the technical details for a moment, the picture becomes almost startling in its scale. Tiny asymmetries in rare particle processes may have shaped the entire material history of the universe. Fleeting excitations that live for almost no time at all can still reveal fields that fill all space. A detector buried underground can tell us something about why stars and bodies and planets exist. The microscopic and the cosmic are not separate dramas. They are one story told at different resolutions. That perhaps is one of the strongest reasons these topics matter beyond specialist circles. They show that the foundations of ordinary life are tied to events and laws so strange that even experts must proceed with caution. There is also a modest ethical lesson in it, if one dares use that word in physics. The lesson is humility. Not the false humility that performs confusion as sophistication, but the real kind, the kind that comes from discovering that reality is under no obligation to fit the first vocabulary we brought to it. Human beings are smart enough to build colliders and subtle enough to measure tiny violations of symmetry. That is no small achievement, but those same achievements keep teaching us that our initial intuitions are parochial. The world is larger than the forms of thought that worked well on the savannah, in the kitchen, or in ordinary daylight. The right response is neither despair nor mystical surrender. It is disciplined wonder. And wonder, when disciplined, has a different texture from fantasy. Fantasy wants the easy astonishment of impossible conclusions. Disciplined wonder is willing to stay with the harder truth. The particle was not there before it was made. The future does not casually rewrite the past, but the measurement context still matters in non-classical ways. Antimatter still carries a formal relation to time reversal. The laws still turn out to be more symmetric and less symmetric than intuition would have guessed in different places. Matter still survives because of tiny imbalances whose full origin we do not yet fully know. That version is slower, less flashy, and far more rewarding. So what does the paradox really mean? It means that the universe does not break causality in the cartoon version. but it also does not preserve our ordinary categories untouched. It means that time is not merely the sequence we live by, though it certainly is that. It means that reality can be lawful while remaining conceptually difficult. It means that some of the most important truths are known only indirectly, through traces and asymmetries and statistics. It means that the world is not constructed for immediate human readability. It must be interpreted, reconstructed, and sometimes described in languages that strain against everyday thought. And for us, perhaps the most personal consequence is this: we can go on living in ordinary time without embarrassment. We can still trust the kettle, the sunrise, the deadlines, the seasons, the way memory falls behind us and plans gather ahead. Physics has not stolen that from us. What it has done is place that ordinary life inside a larger and stranger frame. The world in which we wait, age, choose and remember is real, but it is suspended over depths that do not always share our neat intuitions. Under the calm flow of daily sequence lies a structure of fields, symmetries, violations and probabilities that makes the familiar world possible without being reducible to familiar terms. So perhaps the final mood here is not alarm but perspective. The paradox turns out not to be a door into nonsense, but a signpost towards subtlety. It warns us against taking ordinary intuitions as universal law. It reminds us that even time, the most intimate background of experience, becomes more complicated the closer we look. And it leaves us with a version of reality that is, if anything, more interesting than the sensational claim ever promised. Not because it hands us time travel or a particle existing before its birth, but because it shows us a universe where the line between the obvious and the deep is far less stable than it first appears. And now, wherever you are listening from, whatever hour it has become in your corner of the world, the clocks around you have gone on doing what they always do. Quietly, steadily, without any visible concern for mesons, symmetries or quantum measurements. Time at your scale still feels ordinary enough. It carries the room into evening, or perhaps into morning, and it moves your thoughts along whether you follow them or let them soften. But beneath that ordinary passing sits a reality that is stranger, more careful, and more subtle than the old simple story allowed. And perhaps there is something restful in that too. The universe does not need to be simpler to be beautiful. It only needs to be real enough for us to keep asking, gently and honestly, what sort of place this is, and what it means to live for a while within its time.